today's session on responsible AI. My name is Chen Tao from TU Delft, the Netherlands.
And I'm Matthias Heinrich from the University of Lübeck. And we would like to welcome the first speaker with a presentation entitled STNAGNN, Data-Driven Spatial Temporal Brain Connectivity Beyond FC, presented by Ziyuan Wang.
The second one.
Is it good?
No, the second one.
Okay, sorry.
Not in order.
Yeah.
This one?
Yes.
Okay.
All right, thank you.
Do you like the... yeah.
Yep.
Yeah.
That's good. Is there anything? All right. All right. Hi, everyone. Thanks for coming in early in the morning. My name is Jiao, and I'm here to present our paper titled Data-Driven Spatial Temporal Brain Connectivity Beyond Functional Connectome. And I used a different title here for the presentation because this is part of our effort to develop an explainable and spatial temporal analysis of fMRI, particularly for our application in the autism spectrum disorder. So here's a list of content that I intend to cover today. I will start with our motivation in the clinical application and the two data sets we used for analyzing the fMRI data, and followed by how we formulate the problem as a spatial temporal graph and how we design our method accordingly, especially how we take advantage about some unique properties in this specific application. After that, I have some tables and figures to show the results and interpretation of our method. And in the future work, we will see some limitations of our current approach and where we would like to do further in this direction. So, as many of you may already be familiar with, autism spectrum disorder is a neurological developmental condition characterized by impaired social interactions, difficulty in communication, and repetitive behaviors. According to the CDC, only in the US, there are about 1 in every 31 children aged 8 years old that has been diagnosed with ASD, and they suffer from heterogeneous symptoms. Early diagnosis and early intervention can really make a difference in the outcome of these patients. However, it is difficult to collect high-quality data from these ASD patients due to their impaired social and communication skills. At this stage, the functional neuroimaging modalities like functional MRI actually offers vast opportunity in developing some robust and also effective method in doing both ASD diagnosis and some biomarker identification. So for this study, we used two data sets. And the first, the BioPoint one, is our private data set, which contains 118 subjects and their task-based fMRI scans. This dataset contains 75 ASD children and 43 age and IQ matched healthy controls. And the task stimulus we used in data acquisition includes 12 videos in two categories. 6 of them are the biological motion videos, and the other 6 are the scrambled motion videos. As you can see here in figure 4, the biological motion videos are human figure movement, like doing hand waving and all sorts of different, the potentially socially meaningful motions. And the scrambled motion videos are just random point light motion. And the scrambled motion videos was, by design, a control group compared to the socially meaningful responses. And the whole task scheme was designed to highlight the differences in processing social information. On this data set, we experiment on the ASD classification task and identifying potential biomarkers for ASD. The other data set we use are the Human Connectome Project data set, which includes fMRI scans from more than 1,000 healthy adult subjects. And for each subject, we have 7 different task-based scans from different categories, including emotion, gambling, and language, etc. And for this data set, we experiment the proposed approach for a brain state classification task. Basically, it's just given an fMRI, determining which task stimulus were used during the data acquisition. And so as we mentioned in the title, we use a spatial temporal graph as input to our model. And here, let's forget about the spatial temporal part for a second and see how we construct a brain graph from the 4D fMRI. So as a start, we need to find a brain atlas with n number of ROIs. And then we parcelate the image into these regions and then average across the volume of each region to get a 1D time series data of the region. And in practice, we actually only average across a randomly sampled 1/3 of all voxels as a data augmentation. And after getting this 1D time series data, we compute a correlation between each ROI and construct a functional connectivity matrix from these correlations. And to construct a graph, we use the strengths of this functional connectivity as node features and edges. So in order to make this whole design spatial temporal, one simple perturbation we can do is to, instead of doing everything on the whole time series, we can truncate things into subsequences of sliding windows. And that way, if we construct a graph from each of the subsequence, and then we can get a spatial temporal dynamic graph. And in figure 5, we have a little bit more detail about how we do this spatial temporal graph in the BioPoint dataset. So actually, we took these sliding windows that are aligned with the 12 video stimulus that were used in data acquisition. And for the node features, we compute the Pearson correlation between ROIs in all of these local sliding windows. But for edges, we actually use a concatenated sequence from all the fMRI signal acquired during the biological motion video stimulus, so that each sliding window actually used a shared set of static edges, which we found would be like a better method in terms of like empirical evidence. We show some statistics about different graph construction method in our ablation study. And when we have like a graph structured data as input, a graph neural network becomes an intuitive choice of model. GNNs has been widely applied in different applications, including analyzing social networks and protein-protein interactions. Among different applications, node permutation invariance and computational efficiency on large graphs are two important considerations for a lot of GNN designs. But for functional brain graph, the node permutation is fixed because we are always using a fixed brain atlas, which allows us to embed some absolute position of graph nodes and edges into like the node features. The second observation is that for the same reason, because we are always using the same brain atlas, we always have fixed and limited number of nodes, which enables us to do some spatial temporal global aggregation without worrying too much about the memory consumption. So based on the two observations, we have our graph neural network architecture to do a multi-scale information aggregation in 2 steps. So for the input sequence of graphs from G1 all the way to GT, we first compute 2 layers of graph convolution based on the predefined spatial edges. And after the 2 graph convolution layer, we add spatial temporal positional encoding to the node features and compute a node-wise self-attention across all spatial temporal nodes. And then for the local information aggregated after the first layer of graph convolution and the global information aggregated after attention, we compute min pooling and max pooling on the graph level to get as a readout function. And then we concatenate the graph level readout and compute a classification label based on a multi-layer perceptron. And in this process, we used a 2D spatial temporal positional encoding here to encode the spatial temporal information of each node, which basically is a multiplication of 2 sinusoidal functions, which the first one encodes the spatial position and the second one encodes the temporal information. And in figure 7, we show a visualization of this proposed encoding and how it aligns better with the spatial temporal structure of the data as compared to 1D raster sequence. And for this proposed architecture, we experiment on 2 different tasks. The first is the ASD classification on BioPoint dataset, and the second is the brain state classification in HCP. And in both datasets, our proposed architecture outperforms these compared temporal GNN baselines. And you can see, which is evidence showing that it is effective to combine the graph convolution with attention algorithm in the spring graph application. And beyond this improvement in accuracy, we also evaluate the trained models on the biopoint dataset to identify potential biomarkers of ASD. And here you can see we used a post hoc explainability method called GN explainer, which from this model we can derive an importance score for each spring region and how much information they contain during each sliding window. And from figure 8, the heat maps shows the importance where the darker regions are more important for getting the classification output. And from our observation, the left parietal lobe and right thalamus appears to be two recurring important regions across different time windows. And also, if we compare the two different task stimulus, the biological motion video and the scrambled motion video, we find that the fMRI signal acquired during the biological motion stimulus, which is in the bottom row, overall speaking, having a higher importance as compared to the control group scrambled motion, which from another perspective verifies the data acquisition choice. And there are still a lot of limitations in our current approach. So if you remember this figure here, when we are constructing the spatial temporal graph, we still used a static set of edges across different sliding windows because the edge construction becomes very noisy if the fMRI sequence is short as in a sliding window. So there are several things that might help with this process. We could directly denoise the fMRI data, getting a clear measurement of correlation, or maybe we can optimize the edges on a graph level based on some geometric convexity constraints. And we could also incorporate some multimodal information, including T1, T2, using structural information as a prior to construct more biologically meaningful edges. And the other thing that we briefly touched on but not dig anything further was to investigate the correspondence between the external task stimulus and the brain responses. So in the current approach, we incorporate some implicit awareness of task difference by using a aligned sliding window choice. But what we really would like to do further in the future is to create a correspondence between the semantic meaning of task stimuli and the corresponding brain stimulus. For example, when people see a hand-waving movement, what does that stimulate the brain response in specific regions? And yes, that wraps up my presentation, and I'm happy to take any question from here.
Thank you a lot for the nice presentation and also for being on time. We have a couple of minutes for questions. Maybe I can start because I don't see anyone yet. So you mentioned that the graph connectivity or the functional connectivity converted into the graph that might cause some problems if the adjacency matrix isn't covering all the edges correctly, right?
Yep.
And then you propose both this using graph attention networks compared to GCNs, but also the node-wise self-attention. Do both of them work together, or is one of them more important than the other?
Yeah, I think they are both important in my opinion, but they aggregate things from two different perspectives. For the graph convolutional networks, they work on the predefined spatial edges. So it's a very local information aggregation that only like aggregates things within like the same sliding window within adjacency of nodes. But the global attention allows like any one node to talk to any other nodes in the whole graph. And the aggregation is based on a fully connected network, which the weights was assigned by the similarity between their node features. So it's a two different scale.
And that's also for temporal information?
Yes.
Yeah.
Mm-hmm.
Can you guys try to get closer to the mics when you talk?
All right.
Thank you.
No problem.
Maybe I can continue with another question. You also compared LSTMs and transformers for modeling the temporal aspect. They're quite similar in the results? Do you have any feeling like whether it makes sense to use transformers or LSTMs in this sense?
Yeah, have very similar results, but using transformers is slightly better. And what I think that it ends up, the advantage of our proposed approach is that we allow a node level explainability to, like, if we go further to, here we only like evaluate the importance of each node, but with attention, what we can do is to evaluate the attention between each of these connectivities, finding out like what network connectivities actually contributes most to the result. And that's something that the RNN structures are limited to.
Great. So we have one final question from the audience. Please go ahead.
Thank you for your presentation. My question is, according to your architecture, I found there max pooling and min pooling are present at the same time. I was wondering why you do so, because in general, why not just use max pooling only or min pooling only?
Yeah, I think that's just the empirical architecture design, like using both bring out better performance than using just one.
And another question is, I assume the data you use are precursor, but I was wondering, because these data are collected from different sites, is there any side effect removal technique you use during pre-processing?
I think you mean for the HCP data.
Yes.
Yeah, we didn't do that. We would just do a direct random bootstrapping, like sampling of cross-validation across all the samples that with all 7 task-based data scans.
Thank you so much.
Yeah, no problem.
All right, let's thank the speaker again and move on to the next.
So let's welcome the next speaker, Abdurrahman Ali Mohammed. I hope I pronounced correct. For count explain interpretable cell counting with prototype-based density map estimation. It's a cool name.
Okay, good morning everyone, and thanks for the introduction. My name is Abdurrahman. I am from Iowa State University, and today I'll be talking about our paper titled Count Explain, which is an interpretable cell counting method, which is prototype based. But before I go into Count Explain, I want to talk about the importance of counting cells, and also why we do density map estimation instead of detecting the cells and counting them. So cell counting, as we all know, is very important and is part of diagnosis or treatment evaluation or different biomedical research. And currently a lot of biologists do manual cell counting, which is very tedious, prone to errors. And it's obvious that we need to automate this process. And to automate the process, the first thing that comes to our mind is segmentation or detection. But the problem with these approaches is it needs a lot of fine-grained annotation. We have to draw bounding boxes or pixel annotations. And they also struggle when it comes to overlapping cells or super clustered or dense cell distributions. So that's where density map estimation comes into play. And it has been shown that density map estimation can perform better than these approaches in different settings, such as crowd counting, object counting, as well as cell counting. So what density map estimation does is it predicts a 2D density map, which shows a heat map of where the cells are located at. And to obtain the total number of cells, we just sum up the pixels of the predicted density map. So each pixel in the density map shows what's the density of the cells at that location. So a generic density map estimation model takes in an input image, uses some convolutional layers, pooling layers, and outputs a density map, which we can sum up the pixel of and get the total count. And the question we ask is, this is not transparent, so can we add transparency to the density map estimation models? So we come up with count explain. So we need some prototypes which represent what cells look like and what other non-cell artifacts look like. And then can we compute the density map based on this information so that we can have a transparent model that can count cells. And with that, we present count explain, which is a first prototype-based interpretable density map estimation framework. And besides the architecture, it also has loss functions that are specific to this use case that enforces meaningful prototypes as well as their diversity. It maintains state-of-the-art counting performance, and we also confirm that the prototypes represent valid cell visual features by performing a small preliminary expert survey. So with that, I will start talking about the architecture of count explain. So in count explain, we start off with a pre-trained feature extractor that is composed of convolutional and pooling layers. So we take in an input image, we pass it through the feature extractor, we get feature maps. Then those feature maps will be normalized using a feature processing layer, which is composed of one convolutional layer and an activation function that brings the values between 0 and 1. Then we come to the prototype layer where the interpretability happens. So the prototype layer has K prototypes, which are divided into two groups. First group represents cells. The other group represents non-cell artifacts. It could be any background, any debris, or other lines in the image that we are not supposed to count. So once we have the prototypes, these prototypes are randomly initialized vectors. Each prototype is a 1x1 vector, randomly initialized. We calculate the similarity of each prototype to the processed feature maps. So for each prototype, we get one similarity map that has the height and width equal to the processed feature maps. So if we have K prototypes, we obtain K similarity maps, which are indicated in the green and blue squares. So we have K prototype similarity maps. Next question is, how do we end up with the predicted density map? So we take the similarity maps from the cell prototypes and we pass them into a density estimation layer, which has convolutional layers that aggregate the similarity maps into a density map. So what this density estimation head is doing is that it finds the right weights to combine the similarity maps that come from the multiple cell prototypes that we have. So once we pass our similarity maps through the density estimation layer, it gives us a predicted density map, which we can sum up to get the total count. So a small recap of the architecture, we start off with a pre-trained convolutional feature extractor, and we process the feature maps to normalize them. Then our prototype layer, which has K prototypes, half of them for cell and the rest for background or non-cell artifacts. We compute the similarity maps for each prototype, and we pass it to the density estimation layer, which gives us the density map. Along with the architecture, we also need some loss functions to ensure that the prototypes are learning relevant features and they're not also collapsing, focusing on one type of visual feature. So we have a multi-objective loss, which is composed of 3 losses. First one is the density estimation loss, obviously, because we are doing cell counting and we want to make sure that the predicted cell count is equal to the ground truth cell count that we have. So this is the regular mean squared error loss. The next one is the prototype to feature loss, which ensures that cell prototypes learn features related to cells and background prototypes learn features related to backgrounds. And how do we ensure that? We say, okay, for cell prototypes, the distance between the prototype and the feature maps at points where cells are located at should be as low as possible. And for background prototypes, the distance between the background prototype and the feature maps at points where there is no cells are located at should be as low as possible. In other words, cell prototypes should look like cells, background prototypes should look like background or non-cell artifacts. So this makes sure that we learn visual features important for cells and background, but there is a high risk of collapsing, meaning all prototypes will focus on the same features. So to avoid that, we introduce diversity loss. So what diversity loss does is, for a given group of prototypes, for example, cell prototypes, we calculate the pairwise similarity between them, and we say, okay, if the similarity is beyond a certain threshold, we have to penalize the model. So that ensures that the model does not have prototypes that are collapsed into one set of visual features. So we combine these three losses with different weights, and we calculate our total loss. And then now I'll go into our experimental setup. Unfortunately, in density map estimation based cell counting, we have data sets with very small number of images, but we try to choose the representative data sets. First one being IDCIA, which has 119 DAPI stained fluorescence microscopy images, and it has blurred cells or highly clustered cells and high count of cells. And DCC has different types of cells and diverse conditions. And we also compare ourselves with state-of-the-art density map estimation models, as well as interpretable models for regression, but not density map estimation. We use mean absolute error as our comparison, and this is a compressed version of our results table that shows count explain performs comparably with both interpretable and non-interpretable cell counting models. And when it comes to visual interpretations, we can see that for a DCC data set, count explain learns what cells look like, if you can see on the left side, and on the right side, the non-cell artifacts include the hemocytometer lines, or the background are represented by our prototypes. Also on the IDCIA data set, we have the cells, some blurred, some clustered, some individual, represented by our prototypes, and the non-cell prototypes represent the empty regions in our images. So this is the knowledge of the model, indicating that, okay, the model thinks cells look like these and backgrounds look like these. But count explain also enables us to get individual explanations. So for a given image, we can look at the similarity maps for each prototype. The first row indicates the similarity maps for our cell prototypes, and you can see the heat map showing different places with different intensities, showing that each prototype is similar to different spots in the image, and the same applies for our background prototypes. We also conduct a biologist survey where we ask our experts, okay, what do you see in the red boxes? Is it cell or non-cell? And how easy was it to tell? And we get a high agreement among our three experts, and also full consensus on 91% of the samples that we presented to them. And same for the background prototypes. And we ask, okay, what if we remove the prototype to feature loss? And we can see that the model doesn't clearly tell which one's cell and which one's background. As you can see on the right-hand side, it thinks some cells are non-cell artifacts, which should not happen. And we also ask, what if we remove the diversity loss? It might be hard to see, but the top row shows with diversity loss, and you can see that the similarity maps are pointing at different areas of the image where we have our without diversity loss, where all prototypes point to the same cells. So no diversity and the prototypes are collapsed. And we also investigate impact of number of prototypes. And I will conclude by saying our feature works include dynamic prototype allocation, which means we have to determine the number of prototypes automatically instead of setting them before training. And we can also use the model knowledge to improve the performance. And we also want to try multiple cell types per image to see if Count Explain can do that job. I would be very happy to take questions, and I can also explain more during the poster session. Thank you very much.
Thanks for the very nice talk. So we have 3 minutes for questions. Please come to the mic. So I have a question.
Sure.
So you designed this prototype layer, and you also have to pre-specify the number of prototypes.
Yes, yes.
So is that a very critical number? So is that related to the diversity loss somehow?
The performance changed a little bit compared, based on the number of prototypes that we use. So we used our intuition and the complexity of the data set to set the number of prototypes. And we understand that the model would struggle the more prototypes that we have, because we ensure the diversity is also maintained. So the more prototypes, you have to make sure that they're all different. So we tried to stay with minimum number of prototypes so that it won't be hard for the model to ensure the diversity.
Yeah. So it's very interesting to see the visualization. So I saw the prototype. So I saw there's in some prototypes there are cells clustered together. Is that what you intended, or is that an artifact?
So we don't have much control over what the prototypes represent, but the only control we have is our loss function saying that, okay, cell prototypes should focus on where cells are located at. So the model, given the diversity, it learns individual cells or clustered cells. So that is something that we get at the end of it, because we don't have any control over what the prototypes should specifically
And it
learn.
wouldn't impact the number of cell counts in the end?
No, it wouldn't. It wouldn't impact it. Yeah.
So any questions from the audience? Yeah, so maybe then I still have questions if I
Sure.
can ask. So basically you add a layer, so you add more things to learn for this network. Does that boost the performance or negatively suppress performance if you have do ablation without this layer?
You mean ablation without the layers that
yeah,
we add?
so with other things frozen.
So one of the architectures called CSRNet is basically similar to our architecture, but it doesn't have the prototype layers. So we can see that our performance is improved compared to that while we have a few more layers. So we observed that the layers that we add improve the performance instead of hurting the performance. And we also add the transparency to the model.
Okay, one last question.
Sure.
So this gives nice explainability. So is there any way that you could use that to improve the final performance in a sort of, for example, interactive way, or use it as a correction?
Yeah, so one of the ways that we think this could improve performance is that we train a model, we see what it learned, what it thinks a cell looks like, what its background looks like, and based on that we can have more examples, representative examples, that improves the model's understanding of what cells look like. Also, we can use the prototypes as examples to indicate, to tell the model, okay, you have to count cells that look like these. So more of an interactive way of doing cell counting.
Okay. So let's thank the speakers again for the nice talk. And
Thank you very much.
Right, this brings us to our third talk in the session, presented by Rusha Deshpande. Hande from FDA. She will talk about a knowledge-based method for detecting network-induced shape artifacts in synthetic images.
Not a good sign.
Yeah, can you duplicate the screen or just drag it over because it's extended? So grab the top bar and drag it over to the second window.
Good morning, everyone. I hope I'm audible. Perfect. My name is Rucha, and the title of my talk is A Knowledge-Based Method for Detecting Network-Induced Shape Artifacts in Synthetic Images. And this work was done at the FDA. So generative models in biomedical imaging are a very popular topic in research. And particularly, unconditional generative models have been quite popular in data augmentation applications, in silico modeling as object models, and also in image reconstruction for object priors. And generally, an unconditional generative model takes in, or rather transforms, random noise. And once it is trained, it can produce images which are similar to those from the training data set. However, when it comes to generative models, hallucinations is a big problem, and it is this capacity of generative models, deep generative models, to generate images, which also gives them the capacity to make errors. And two examples of errors are on the screen. So in the first image, we can see it's an image of the eye fundus, and typically we would have one optical disc, but in this case, we can see that the generative model created two optical discs, which in this case is not anatomically realistic. In the second image of a chest X-ray, we can see that there are wire connections going from nowhere to nowhere. There are attempts at creating support devices, which are, again, not realistic. So in the literature, it has been shown, or it has such instances of errors have been reported multiple times. However, when it comes to detecting image level artifacts, so being able to flag individual images, that's an underexplored area. And commonly when it comes to generative models, people end up using popular distribution level evaluation methods. But these methods are insufficient for flagging individual images with network induced artifacts. And so often these synthetic data sets are very large data sets, so there are hundreds of thousands of images even. And so when it comes to detecting artifacts, there are several challenges. So one challenge is that if we are going to visually spot check, it's possible that low prevalence artifacts might be missed. Then again, the artifacts themselves are unknown, so we don't know what the network is going to put into these images. Artifact labels are often unavailable. And then again, these artifacts might vary depending on the generative model paradigm that's been used. And lastly, there are domain-specific factors depending on the anatomy or the imaging protocols. So even though synthetic data sets have a lot of potential, if they are used without evaluating their quality, we risk impacting their clinical utility and the model performance. So in this particular work, we focused on shape artifacts, so detecting shape artifacts in synthetic images. And as an example, we used synthetic mammography images, although the method is generalizable to other imaging modalities as well. So there were two main data sets that we used. The first one was Seesaw-M, which originates from Sweden. The other is WinDR, which originates from Vietnam, and about 10,000 images in each data set. Used MLO or mediolateral oblique views only, which is essentially a side view of the human breast. And then we had matching synthetic data sets corresponding to each patient data sets, which were generated from two different generative modeling paradigms. So one was a latent diffusion model, and the other was a GAN model. So this is an overview of the whole method. We start out with matching data sets at the input. So we have a patient data set and we have a synthetic data set. As part of pre-processing, we create masks and then we extract the boundary of this, the region of interest or the shape of interest. Then the innovative part is the feature space construction. That's the core, where we created a purposefully designed feature space which is also interpretable. And thus we can incorporate knowledge-based information or knowledge-based features in understanding what kinds of mistakes are happening. So more specifically, once we have the boundary, we track the boundary and we represent it in terms of the angular trajectory, followed by the gradients between the successive angles. So we have a gradient of the angular trajectory. And then we summarize it in two ways. First is a bin-wise summary, which allows for a generalizability across variations in breast sizes. And it's also a choice between whether we want to capture more local artifacts or global artifacts, and it's something that you can tune. Finally, we have a per image summary. So what that allows us to do is to represent how often certain changes occur. So for example, in the nipple region, you'll have a very sharp change in the gradient. But that kind of change happens only once within each image. So that's what we are trying to represent. So if we get a higher frequency of that change, then that indicates an artifact. So we have a bin-wise summary followed by a per image summary. And at the end, we have a 16-dimensional vector representing the shape. Once we have the 16-dimensional vector, we input that into an anomaly detection algorithm called the isolation forest. The isolation forest is a very lightweight, robust algorithm which essentially recursively partitions the feature space until we can isolate individual data samples. And the number of partitions it takes to isolate a data sample is indicative of how unusual or how anomalous the image is. So based on this, we get an anomaly score and we get a distribution of rankings on the synthetic data set. And for validation, we compare these anomaly rankings against those from human or reader studies. So looking at dataset level results, so for the two data sets, what we have on the screen here, the way to understand this plot is on the x-axis, we have bins along the breast boundary. So from left to right on the x-axis, we are following this trajectory from the chest wall to the nipple region and to the end of the breast region. And the dotted line indicates the mean, and the shaded region represents one standard deviation. So what we have on the y-axis, the actual values, are the per bin cumulative sum of angle gradients. So we can see that there are less changes leading up to the nipple region, but there are high changes, high variance in the nipple region, followed by again lower changes in the end of the breast region. So two main takeaways from this point, from this slide. The first one is that the purple and the orange distributions, that is respectively the real and the synthetic distributions, do not exactly match in both cases. And in fact, in the second data set, we actually see that the mean breast shape in the synthetic region is different from that of the patient distribution, which indicates a bias in shape in the synthetic distribution. The second takeaway is that just if we look at the patient data sets themselves, so just the purple distributions in both cases, we can see that they themselves are different. And so that could be possibly indicative of the demographic differences, given that one of these data sets was from Sweden and the other from Vietnam. Then looking at quantitative results, we have this distribution of anomaly scores, which is output from the artifact detection algorithm. We see it as a tail distribution, indicating that there are fewer images that are anomalous. And then we choose images from 3 partitions that we create just to be able to inspect these images. So we have the first percentile, the first to the 10th percentile, and then the remaining percentiles. So these percentiles are created based on the rankings given by the anomaly score. So if we look at the actual images, we can see all kinds of problems in the first percentile. So we have instances of multiple nipples, we have instances of oddly shaped chest wall connections, we have badly formed nipple regions, and in another data set, it barely looks like a breast at all. The intermediate partitions show fewer such errors, and then the 10th to the 100th percentile is essentially normal images. Then we validate this method via reader studies. So we choose 10 images from each of these partitions randomly, and we design a 2 alternative forced choice study from based on these partitions. And the question we asked is, of the 2 images shown on the screen, which of the 2 images is most anomalous in terms of shape? So what we saw was that there was good agreement between rankings from the algorithm and the readers. The percentages shown in this table indicate the percent trials when an image was chosen as most anomalous. So if the algorithm didn't work, we'd see 50% across the board. But what we are seeing is a trend where the first partition was almost 1.5 to twice often as chosen as the last partition, at least the mean values. And that indicates that humans did think that the anomalies were effectively concentrated in the first partition as opposed to the last partition. And these trends were similar for both data sets. A little bit on the side, so although we created this method to evaluate synthetic data sets, it can also be applied to discover naturally anomalous images purely in the patient data set. So some examples that we saw were examples of surgically transformed breasts, or thin breasts, or breast fold artifacts, or malignancies, and so on. So in summary, this method can identify images with unrealistic anatomical shapes. It can greatly improve the efficiency of visual search, and essentially it can be used as a first pass if you're trying to create labels for any self-supervised or supervised methods downstream. This method is model agnostic, which means you could use any generative modeling paradigm, or you could even use traditional knowledge-based methods, or any kinds of data sets, any kinds of 2 data sets which are similar in some sense. You do not need examples of artifacts in your training data. So this method will still be able to identify artifacts that were never seen in the training data. And lastly, it is interpretable because of its knowledge-based design. So you can pinpoint where the mistakes were and what kinds of mistakes were seen in terms of shape. So in the future, this method can be generalized to other imaging modalities and tasks such as synthetic brain CT or pathology images, as long as you have access to segmentation masks. The other direction that we're currently pursuing is a complementary direction focusing on breast tissue texture to be able to identify network-induced texture artifacts. And lastly, we're also exploring the task-relevant impact of these artifacts that we have discovered. So that's all from my end. Thank you so much, and I'm open for questions.
Thanks a lot for the great talk. Ron?
Thanks very much for your talk. What sort of things would one have to do to apply your method to other types of images?
Mhm.
If you could just speculate on that.
So right now the code is publicly available. So you can download it. It's hosted on the FDA website. The first thing you would need is segmentation masks for your data sets. Secondly, you would have to ensure that the orientation is consistent within your data set. And then you would have to, I think the technical backbone you could use as such, because essentially you're characterizing the distribution of angles for that particular shape. And so you're seeing how different are the two distributions of angles which characterize my shape. So it will work as long as there are consistent orientations and reliable segmentation masks.
Thanks.
Thank you. Oh, and be happy to talk afterwards and customize it for your own case if you like.
Maybe I can continue with maybe a critical question, even though I really like the approach. If you are really good at detecting anomalies and you use that for the synthetic data, aren't you getting rid of some real anomalies and then make your data set less diverse in the end? So it could be like a downside of it?
So that's an excellent question. So two parts to that answer. Firstly, there could be anomalies or less common images in the patient data itself. So we fit the anomaly detection to the patient data set. So it is the user choice whether they want to leave out the anomalies in the data in the patient data set or not. So if they don't leave those out, the same will be reflected in their synthetic data set. So you can choose to keep them. Secondly, if you're looking at just the anomaly rankings within the synthetic data set, so it's a ranking, it's not a binary decision. So the user can decide the cutoff point where they want to consider anomalies, what they consider as an anomalous region versus normal.
It's really nice work. I want to follow up with a critical question. So I wonder what these unconditional generative images can be used for if they, well, basically don't add more information, but additionally may bring some hallucinations. So I'm just curious how that can be used for in training models or clinical practice.
So generally I'm seeing two main areas at the moment. One main area that people want to use unconditional models is data augmentation. And yes, you're right that we are not creating new information in a sense, but sometimes it could be more examples of the kinds of things we want to see. But at the same time, we want to eliminate the exposure of the model to the kinds of variance that's not natural. So that's one direction. The other quite popular direction is actually in silico modeling and digital twins. So when it comes to designing virtual imaging trials or in silico tests, what I'm seeing is people there are two ways to do it. So instead of creating completely knowledge-based mechanistic models, people tend to use generative models to replicate the distribution and then tune those parameters to create a virtual population cohort. So those are the two main directions right now.
All right, let's thank the speaker again.
Thank you.
So let's invite the next speaker. Again, Mario Favero, sorry. Conditional diffusion models are medical image classifiers that provide explainability and uncertainty for free. Interesting.
All right, thank you very much. Good morning, everyone. My name's John, and I'm here from the Probabilistic Vision Group at McGill, which is in the sovereign nation of Canada. I'm pleased to be presenting our work, which is joint with my co-authors Parham, Emily, Brennan, and Dr. Tal Arbel, who also leads the Probabilistic Vision Group. Deep learning-based classifiers have become foundational tools in healthcare, showing the potential to revolutionize patient outcomes. For example, from chest x-rays, discriminative classifiers can detect signs of diseases such as pneumonia, lung cancer, or heart failure with impressive accuracy. However, the usage of deep learning in critical settings like healthcare brings unique risks that open the door to various sources of danger if not addressed properly. For example, what is a classifier looking at to make its prediction? In the example we show here on the right, we've highlighted some potential image components that a classifier might use to determine if a patient is healthy or has a certain disease. In this case, pleural effusion. In literature, it's been shown repeatedly that when unchecked, deep learning models can make very trivial decisions, like making the decision that a patient has a certain disease based on if they're wearing a medical device or if certain text appears in the corners of the image. A good model needs to first and foremost make the correct decision, but also provide the correct reassurance why it is making that decision, which should be the presence of the disease. Another important detail that goes missing when using deep learning tools in isolation is a measure of uncertainty. In medicine, doctors rarely make decisions with absolute certainty. They weigh evidence, consider alternative diagnoses, and express how confident they are before deciding on treatment. A model that simply says disease without revealing its confidence might mislead clinicians into thinking the result is definitive, even in ambiguous cases. So as such, a good model should not only make accurate predictions, but also provide a measure of certainty, and importantly, a good model should be more accurate in its more certain predictions. Now, there have been efforts made to improve discriminative classifiers on these fronts. However, current explainability and uncertainty methods depend largely on post hoc analysis or model modifications, and these have various levels of efficacy. On the explainability front, we often rely on gradient-based analysis after training, like GradCam, or more recently, counterfactual generation with a separate generative model that is guided by the classifier itself. On the uncertainty front, methods range from model modifications like Monte Carlo dropout to expensive ensembling methods. So nonetheless, discriminative classifiers alone cannot explain why they make their decisions or provide reliable uncertainty estimates suitable for safe clinical use. Nowadays, diffusion models have certainly become a jack of all trades, starting somewhat of a revolution in computer vision. And what we'll show today is that these types of diffusion models themselves can be repurposed very simply to solve the problems I've highlighted on the previous slides. We can start by recalling the training objective of these types of models. Behind a lot of complicated math, diffusion models are glorified denoising networks. The key difference is that with diffusion models, images are corrupted at varying signal-to-noise ratios, which the model is conditioned on. In other words, the model is aware of how corrupted the original image is while denoising it. The job of diffusion models during training is then to take a corrupted image, take an indication of how noisy it is, and then predict the clean version. These models are trained in a simple and stable manner with a mean squared error loss on the reconstructed image. There are some caveats here, like signal-to-noise ratio distribution and loss weighting, but we can afford to leave out those details here. A conditional diffusion model trains in the exact same manner, although now with an additional condition that should help the network denoise the image easier. Take, for instance, the chest x-ray in the top left, and that the patient could be of one of two conditions, sick with pleural effusion or healthy. Knowing the condition of the sample, in addition of course to the signal-to-noise ratio, should help the model with its prediction. By the end of training, the model would have seen patients with all conditions and at a wide range of signal-to-noise ratios. And as we will see, this training setup allows us to use conditional diffusion models and other very helpful ways in medical imaging aside from just generative tasks. In our case, we highlight that one of these applications is that conditional diffusion models can be very easily converted into a classifier. How exactly can we do this? Well, we can consider one denoising step from the model in isolation. We turn the model's denoising task into a competition. Which condition helps it denoise the corrupted image the best? In this example, we've dropped the signal-to-noise ratio condition but for clarity, know that it's still there. So let's say we have a corrupted image and a set of two conditions, sick or healthy. For a given signal-to-noise ratio, we can make a denoising prediction with the model on both possible conditions and see which condition allows the model to have a better reconstruction error. Now we should be able to see how this could work on a high level. By comparing reconstruction errors on both conditions, we pick the condition that results in the lower error, but some key details remain. For example, what is the right signal-to-noise ratio to use for predictions? And given that diffusion models are stochastic, how many different inferences should we use to make a prediction? Effectively, we can try many inferences at various signal-to-noise ratio levels all across the spectrum, and I mean from almost no corruption to almost fully corrupted. And as it turns out, when the amount of inferences is sufficient and aggregated appropriately, we can extract a very competitive classifier from a conditional diffusion model. An important question is, how should these many inferences be aggregated in order to make the final prediction? We considered two options, which we call reconstruction error and majority voting. With average reconstruction error, we simply add up the reconstruction errors for the n inferences for both classes, and then at the end, choose the class with the minimum total error. For the majority voting alternative, we consider each inference to be its own individual prediction. We tally the number of votes that each class gets, and then at the end, we select the class that has the most votes as the prediction. Now, armed with these ideas, we can see how diffusion classifiers actually work. We conducted our experiments across three widely used diffusion model architectures, the ADM-UNet, the diffusion transformer, and stable diffusion foundation model. We trained the UNet and diffusion transformer models from scratch, and we fine-tuned stable diffusion on our specific dataset. We used subsets of two widely used medical image datasets for our experiments, which are CheckSpurt, specifically pleural effusion and no findings, and the ISIC melanoma skin lesion dataset. We find that across all three architectures and on both datasets, majority voting leads to better classification accuracy than average reconstruction error. This result is intuitive. Remember that signal-to-noise ratio values are chosen randomly, so at greater values of n, or with more inferences, there are more reconstructions attempted from high noise disturbance, which can introduce large sources of variance in the average error. As a sanity check, we also tested the degree to which accuracy decreases when less computation is used. We find that overall, more classification steps leads to better accuracy, but there is a plateau in performance for all models, suggesting that there's a trade-off available between inference speed and accuracy if needed. When we compare our diffusion classifiers against state-of-the-art baselines, we find that they are indeed competitive. Admittedly, they're not the outright best, but they're well within striking distance or better than individual baselines. Importantly, our diffusion classifier results are achieved with no data augmentation, minimal hyperparameter tuning, and using a simple and stable mean squared error loss function. The same cannot be said for the discriminative classifier. However, to truly see the advantages of these types of models, we move towards two key topics alluded to prior: explainability and uncertainty estimation. Now, once training is complete, we still have a class-conditional generative model that can produce or edit samples. We use basic diffusion model editing techniques to generate counterfactual images of patients to determine the key differences in the images when a condition is changed. In this case, turning a sick patient into a healthy one. Right out of the box, a diffusion classifier can make a prediction, sick or healthy, and then provide qualitative reason for why the prediction was made. Finally, since diffusion models are stochastic, we can make some easy analogies to ensembling. We take advantage of the fact that we make n inference steps to produce an estimation of uncertainty. We first form a distribution over category labels with our predictions for a given sample. Then, using entropy, we can get a measure of uncertainty from this distribution. Most importantly, we test that the uncertainty measure provided by the model is clinically significant. That is, high confidence predictions from the model are more correct, while uncertain cases can be flagged for further testing or expert review. We confirm this by filtering out the most uncertain predictions and examining the change in performance on the remaining samples. Excitingly, performance improves as the most uncertain predictions are filtered out from each of our diffusion classifiers and on both datasets. So if I can provide some final thoughts, today we saw that diffusion models can be repurposed as classifiers, diffusion classifiers are naturally explainable, and that diffusion classifiers are uncertain when they're wrong. And thanks for your attention. With that, I can open it up to any easy questions.
Thanks for the great talk. We have 3 minutes for questions.
Thanks for your presentation. I just have a quick question for the for explainability. You just mentioned that you show the counterfactual heat map over there, right? So the heat map shows the visualize the pixels or the regions they use to make different decisions. But how is this explainably useful, right? How is it useful for physicians or medical doctors? How this can help them to explain the results? I just wonder why. Yeah.
Okay, so the question is, given a prediction and then this heat map of difference, how can that help a clinician?
Yeah. How is this going to help the explainability, right?
Right.
Yeah.
So when you make n classification steps and you have a final prediction, it's important to know where the model is looking at when it makes that prediction. So for example, if it's just looking at if the person has a medical device or if there's certain text in the corner of the image, like you know that there's a shortcut there and it's not actually looking for the disease. But when you go back and noise the image and then change the condition and edit it, you can see what the model is actually looking at when it's given those conditions.
Yeah.
So in this case here, we can see that the original patient is sick with some fluid in the lungs. I'm not a radiologist or an expert, and then when you edit the image and give it the healthy class, you can see that what it actually does to make the person healthy is remove that fluid from the lungs. So this is a post hoc explanation for what's actually changing, how the model reasons if the person's sick or healthy.
Yes, but at the very beginning of your slides, you mentioned that that's one of the major limitations of the current approaches, right? The post hoc approaches. But your approach is also a post hoc approach, right?
But it's a single model.
Yeah.
Yeah.
But I don't. But we probably can discuss more. But yeah, based on we are also working on explainability research. So my understanding is this for the model saliency, the heat map we offered here. After we talk with medical doctors, their idea is that they offer very limited actual information to a doctor. The explainability based on semantic information, for example, why the decision, what specific clinical related information the model can offer, that's probably offer better explainability, right? So for the model saliency or the heat map we offer here, like the counterfactual, probably it's a good starting point, right? But we probably, if we can do more semantic, extract more semantic information or extract more semantic information, that might be more helpful. Clinical related semantic information, right?
For sure, yeah. And this is, again, introductory and exploratory work. But, 100% it should be up to clinicians and people who are actually using this to make it as applicable as possible.
Yeah, thank you.
Thanks very much for a really great talk. Really think that's a very nice idea. I have one hopefully easy question. So you're using sort of the reconstruction error to effectively decide which one is a better, which class it should be. And I guess you're doing that over the whole image, correct? And in some cases, some diseases, you have very focal changes between perhaps healthy and diseased. And I'm just wondering, is there sort of, for those things where you have focal changes, a better metric or an alternative metric you could explore? Because I could sort of see that small changes will get swarmed by perhaps very large areas in the image.
Yeah, it's a good point. And I think Amar, during this PRISM talk yesterday, addressed the fact that we need higher resolution images in some case to address some of these issues when there's minor details that distinguish between clinically relevant things. So I'd say one thing is having an image resolution that is suitable for what you're looking for. And then the way that this works is you're adding noise at different steps, and you're generally just hoping that during your random selection of signal-to-noise ratios, you're averaging out the parts that remain the same, and you're only finding the stuff that's different.
Okay. Thank you.
No problem.
Hi, really cool presentation. One question I had was about handling images in like the multitask settings. So like if you're trying to classify like different types of pathologies like within a single classifier, and like it's very reasonable and possible that you can have images that present with multiple pathologies at the same time. And so with this majority approach, I just wanted to clarify, is that like sort of picking like a single class that's like, okay, you have this condition even though you might have another condition as well, and like and if that is the case, like how could this approach sort of adapt to those cases?
This one's too hard. No. So the way that we designed our experiments was basically so that the patient either had pleural effusion or nothing, like was healthy.
Okay.
And then same with the ISIC, it was either like a melanoma or healthy. So we didn't actually explore like multiple conditions at once. But it's a very good point and something that should be explored.
Okay, cool.
Yeah.
Thanks.
No problem.
Can I ask one final easy question? So I was wondering, do you think this method can give some insight on those cases which are maybe confused either by machine or even by human? Because I think this is a really very intuitive way of thinking about this classification problem.
So sorry, just to clarify, you mean like, can the measure of uncertainty, does it match with if a human's uncertain?
Yeah, for example, maybe the counterfactual way of explaining things. Can that explain how why human or machine can make some mistakes on some cases? Because there are cases which are easily confused. There are always those cases.
Yeah, I think, so the explainability part is going to be, that's one aspect of it, but I think like if it's an ambiguous case, you'd hope that the model's also uncertain. And I think that's probably the more important thing that might connect more with how humans evaluate these images.
Okay. Oh, one more question.
I'm hoping this is an easy question. Can you remind me whether you've adapted this technique to work in 3D as well? I'm thinking applications like CT and MRI scans.
Yeah, so in our paper, we did not do any 3D experiments. We just stuck with more computationally easy 2D. But the fundamentals are basically the same, and as long as you have enough compute and the right convolutional layers, it's adaptable to 3D as well.
What do you mean by the right convolutional?
Like
layers?
3D convolutions instead of 2D, yeah.
Just that, okay.
Okay, great. Let's thank the speakers again.
Which brings us to the final talk in the session. It's also on diffusion models. Can diffusion models generalize privacy, fairness, trade-offs for medical data sharing? It's presented by Misha Dombrovsky, also from a free state, Bavaria.
Okay, so thank you very much for the kind introduction. I'm really excited to be here to present you my paper on the topic of data sharing. So if you look at data sharing, the key motivation is usually a bit different to what you would see from the normal image generation. So the basic idea is we have a hospital with private data, have a hospital with private data, and we want to share synthetic medical data. We want to share synthetic data without the permission of the patients, which is of course very very hard task, and the difference to the normal image generation would be so we rather care so we do not only care so we so we care about the privacy and the fairness aspect of the data sets as well. So if you look at the related work, you will see that privacy is a very famous research area where there exists a lot of memorization issues. However, usually usually you require the training data here to be able usually you require the training data to be able to extract the memorized images. As for and for fairness, on the other hand, you have also famous research problem, but usually usually the fairness only addresses the fairness of using thank you of using image generation models here to solve the fairness, but we do not look at the fairness of the diffusion model itself usually. So we try to change that by looking as image generation as a long tail problem. So usually for these problems you see that here you have a head data set where it is easy to learn the data and then you have a tail data set. So our research really cares. So yeah, so yeah, it's okay. So we so here really care about the far we really care about the far end of the tail. So basically rare image artifacts. So to here show you a few examples. We have a few images. So for example, rare diseases, rare support devices, as mislabeled or unique features. And the main goal would be that so these features would also be part of the synthetic data set if we do data sharing. And essentially there are two approaches now. So we could so we could try to ignore so we could try so we could as we could try to ignore them, or we could try to memorize them, which would lead to which would lead to a memorization issue. Here to a privacy issue. So we show in our paper how to here basically retrieve as to, as we show how to retrieve the training images from the synthetic dataset without access, as without access to the training dataset, as by using prior, as by use. As by using prior information, and so essentially our goal is here now to generalize, which means that we don't want to ignore or want to memorize as the fingerprint, but we want to have as we have the main idea of what we're doing is we're essentially taking a training data set and then we artificially add a fingerprint to it, and then we automatically measure the the presence of the fingerprint in the synthetic data set. And there are basically three outcomes. So, the fingerprint could be forgotten, which you can see here. So you have the same training images or you have a synthetic data set, but the fingerprint is never present. So then so maybe we just here show the generalization. Here, so essentially what we want to have is, as we want to see the fingerprint, but in a different image. Here to sort of avoid the privacy attack, but at the same time to reach fairness. And we measure this using here two classifiers, which I can't go really into detail. Hopefully the image is clear. So we detect the presence of the fingerprint and we detect the identity of the person in the image. And we say that the model, and we say that and we say that the model has learned to generalize if you cannot so if the presence of the fingerprint does not imply the identity, and we do our experiments on 3 data sets and also 3 types of fingerprints, and we and we basically try to achieve generalization by as as by as by also here changing the key factors and I mean the image is a bit a squash but as maybe the main as maybe the main key takeaway so here you can see the main key takeaways, and we have and we have since then worked a lot on solving these issues with two other papers I presented as recently. Yeah, so thank you for the attention.
Thank you a lot. Are there any urgent questions from the audience? Because we're already a little bit over time, I would suggest we take questions to the poster.
Yeah, I go to the poster.
Yeah, thank you a lot.
Yeah.
And thanks all the speakers again from this session. And we take a coffee break.
Okay, let's everybody please settle down and so we can get started and keep on time. If you could please take your seats. Okay, it's my great pleasure to welcome Professor Daniel Ruckert. I had the good fortune to be in Daniel's lab for my sabbatical a number of years ago at Imperial College, so it's a great honor to welcome him today. His field of research is the area of AI and ML and their application to medicine and healthcare. His research focuses on the development of innovative algorithms for biomedical image acquisition, image analysis, and image interpretation, especially in the areas of image reconstruction, registration, segmentation, and modeling. And AI for extracting clinically useful information from biomedical images, especially for computer-assisted diagnosis and prognosis. Since 2020, Daniel is Alexander von Humboldt Professor for AI in Medicine and Healthcare at Technical University of Munich. And if you don't know who Alexander von Humboldt was, I would encourage you to look him up, not now, but after Daniel's presentation. He's a fascinating historical figure. Daniel is also a professor at Imperial College London. He gained his master's from Technical University Berlin and his PhD from Imperial College, followed by a postdoc at King's College. In 1999, he joined Imperial College as a lecturer, becoming senior lecturer and then full professor. And from 2016 to 2020, he was head of the Department of Computing at Imperial College. Please welcome Dr. Daniel Ruckert.
Thank you very much, Ron, for this kind introduction. And it's a great pleasure to be here and give to you this keynote. Let me just figure out how I get to my slides. Perfect. Thank you again. So I have a quite provocative title, AI and the Future of Radiology. I'm not sure I can tell you exactly how the future will look like in this field, but I wanted to give you some ideas in which direction I think the field is moving and what the current state of the art is, and perhaps also give you an outlook to some of the challenges which we're facing in the field. So I'm sure that you have all seen these different newspaper headlines which proclaim a new era in medicine enabled by AI and by machine learning. And I should also say there's probably not only positive spin like here, there's also to some degree a certain amount of hype. I think you probably all know this gentleman, and you probably also know his prediction from a couple of years ago. That self-driving cars will be around in 2 years' time. You probably also know the prediction of this gentleman, who's now a Nobel Prize winner, and he predicted radiologists will be obsolete in 5 years' time. Again, this was a while ago. And you probably also see the reality of what has happened so far. So it's not always not all these predictions come true. And I think at the moment, while there's a lot of talk about AI and the potential in medicine, there is much less realization of that potential than there is perhaps the talk about that. Nevertheless, if you look at a particular field, which I think most of you are interested in, because this is, of course, after all, a medical imaging meeting, AI is probably the furthest along the line in fields such as radiology. And that's, I think, to a large degree that I think radiologists have always worked with digital data for quite a while now. There is a certain amount of digitalization in that field. And so if you look at a survey of FDA-approved devices, these numbers might be a bit outdated, but if you look at the link at the bottom, there's an up-to-date list of that. You see that 3/4 of all FDA-approved AI technology is in the field of radiology. I think that probably also includes pathology. And I think the reason for that is that if we look at the entire potential pyramid or pipeline in imaging where you can actually use AI, there's a tremendous opportunity to use AI across the entire imaging pipeline. So if you look at the top of this pyramid, of course, that's what we're mostly interested in, what's probably the easiest one to write very impactful papers on. We want to, of course, improve the diagnosis and prognosis of disease from imaging. But if you look at the bottom of this pyramid, that's probably where AI has had most impact so far. So if you think about what AI tool is used every day in clinical practice in radiology, it's not at the top of this pyramid, but it's at the bottom, because every MR scanner, every modern CT scanner probably now uses AI in the reconstruction algorithms for producing the images. And so a radiologist might use AI without really knowing that they're actually using AI explicitly. So what I wanted to do today is give you a brief glimpse of some of these AI approaches in these different areas and some of the problems they have, and then talk about some of the challenges we're facing and perhaps what the future might bring. So I want to start with a very simple example of how AI can use accelerate, for example, image reconstruction in MRI imaging. Most of you will be familiar with that. Images in MRI imaging are acquired in K-space, and then we apply a reconstruction algorithm, which I can sort of denote here as a shortcut as a Fourier transform. It's a bit more complicated than that, to reconstruct an image. And that process is relatively slow because we have to sample K-space sequentially, and as a result of that, the image acquisition process is quite slow. Of course, what we can do is we can accelerate the image acquisition process by collecting less data. And that's sort of depicted on this slide, where we're collecting less data by subsampling K-space. You see here I'm subsampling mostly the high frequencies at the outer areas of K-space. And you also see that if I apply a reconstruction algorithm to that data, you see suddenly artifacts from aliasing because we're violating Nyquist sampling theorem. So one of the things we can do, and what a modern MR scanner will do, is it will use some learning-based reconstruction to actually improve the image quality and remove these aliasing artifacts. And there are effectively two versions of this type of algorithm, and I wanted to first show you the older one. At least in our group, we sort of started by first developing these algorithms which treat the problem as a denoising problem in the image domain, and which basically do the following. They basically take your undersampled K-space and your reconstruction with artifacts. They apply an unrolled network which consists of two types of blocks. The first block will denoise the image in the image domain using convolutional layers, and the second block will then apply a Fourier transform to the reconstructed image and actually perform a data consistency operation to make sure that the image you're reconstructing is actually consistent with the measurements you've made in K-space. And then you sort of iterate forwards and backwards between that. And that's effectively unrolling an iterative reconstruction algorithm in a deep neural network. And so this works very well. If you sort of look at some of these reconstructions on this slide, you see on the left-hand side the original undersampled K-space reconstruction. Looks horrible. You also see on the right-hand side the fully sampled reconstruction, and in the middle you can see the deep learning-based reconstructions. And you can hopefully agree with me that they actually look very high quality. You also see here on the left-hand side the reconstruction undersampling rates, and you can see that you're accelerating your acquisition by a factor of 6 or 11 in this particular case, and that's a significant acceleration in this particular case. Now we can do that also with, of course, other parts of the anatomy. We can do this, for example, in this particular case with with brain imaging. This is some work from Carsten Hammernick, who used to be a postdoc in our lab and now works at NVIDIA. And you can see that this also equally works well in, for example, 3D static imaging, not only in dynamic imaging. But we also quite often get questions asked, how reliable is a reconstruction? Does it ever, or does your AI ever hallucinate things which shouldn't be in the image? And so what Kerstin set out to do is to investigate this a bit further and do this by effectively doing a study which you see here on this slide. So what you see here in the middle row are reconstructions which are generated by training on MR neuro images. So MR images of the brain and then reconstructing a brain. What you see in the column next to that is the same algorithm applied, but this time trained with knee MRI images. And what you see in the top case is actually, if you have low undersampling rates, so if you have a lot of data, the algorithm still works, even though your training data looks very different. But if you push it very aggressively, what you see in the bottom case, you actually suddenly see a hallucination of a knee appearing inside the brain. Now, I hope that Ron will agree with me that every radiologist who will see that is probably going to recognize that this is not a horrible accident where the patient's knee ended up inside the brain. But it's also, of course, once you see a hallucination like this, you wonder whether there are other hallucinations in the data as well, which are not so easy to pick up in. So I wanted to take you back to the reason where this comes from, and it probably comes from the fact that we have training data which is not matched to the actual data during inference. So if you sort of think back to this scenario, I said I can denoise the image in the image domain, but I could equally well actually say, well, you know what, I'm going to treat this as an interpolation problem in K-space. I'm trying to find the missing lines of K-space in the K-space domain and interpolate these missing lines of K-space. And what I want to show you on the next couple of slides is an approach which does this, which doesn't use any training data and therefore doesn't have this problem of hallucination. And the basic idea which we're using for this is something which I think in the computer vision community is now quite well known. It's based on something called a neural implicit function, which is effectively a neural network interpolating data. And this has been quite around for some time. So on the left-hand side, you see, for example, a neural network which gets as input x, y, z coordinates and as output produces the RGB values at those coordinates. So if you train a network like this, it will basically learn to represent one single image, but only that one single image. And that approach really is effectively learning a continuous representation of discrete data. And as I said before, this is something which in computer vision people have done for a while to represent images, to represent shapes, to represent, for example, audio signals. Now, how is this helpful in MR reconstruction? Well, one of the things you should probably sort of think about is sort of a bit back to how is MR data typically acquired? And in particular, if you, for example, do this with the heart, you typically acquire data with this ECG gated. That means you're actually collecting this K-space data not during a single heartbeat, but across multiple heartbeats, and you're using an ECG to basically temporarily align the data. So what you can, for example, do is you acquire these lines of K-space, and then you sort of build a single one heartbeat model of these lines of K-space, and they're all at a different point in time. You typically pretend that there are only a discrete number of frames, so you typically bin that data, and then you can perform a reconstruction. But what you can also do, you can actually try to effectively train a neural network to learn a continuous representation of that K-space of that one subject. And this is something which, for example, you can do by taking a normal MLP. This MLP gets as input the K-space XY coordinates. You're also giving it the time coordinate, and you can ignore the C here. This is a coil number because typically in MRI imaging, you have multiple receive coils. And this network is then trained to basically produce a K-space value at those locations which you have sampled in K-space. And what you can then do is you can sort of train this network by minimizing a loss between the prediction of that network at those points and the actual measured value. And remember that this K-space only comes from one single subject. Once you have sort of fitted that network to that subject's data, you can then do inference. And in the inference phase, what you do is you basically define your regular K-space grid. You basically sample every point. You take the X, Y, and T coordinates, and then you effectively apply the network to all of these locations, and you get the predicted K-space value at all of those locations, and then you reconstruct your image in the conventional way by applying a Fourier transform to the data. So in a nutshell, the entire framework looks like this. You're taking your K-space data from that subject, you're training the network on that subject, and then you're doing inference also on that subject. So the beauty of this approach is you don't require training data from any other subject. So it's subject specific and it's not biased towards your training population. There's of course also a downside. You have to train that network from scratch for every subject. So it's not as fast as some of the other methods because they only do inference at the reconstruction phase. But one of the things you can do with that is you can do reconstructions almost in real time. For example, this is reconstruction results from only 4 heartbeats. So you have 4 heartbeats of K-space data. You see on the left-hand side the reference reconstruction. On the right-hand side, you see our deep learning-based reconstruction. In the middle, you see some other benchmark or baseline methods. And you can see actually it works reasonably well for 4 heartbeats. If you go down to only 1 heartbeat, you can actually see that all of these methods degrade quite badly. Even also the method I've just shown you here also now produces not so great looking images anymore, but it actually still looks something which you can recognize and from which you could basically do a basic measurements. So I think that's and if you're doing this with 1 heartbeat, the scan time is massively reduced. You're going from a breath hold of 10 seconds to imaging within 1 heartbeat, which is roughly 1 second. So it's a very significant reduction in scan time. Now, so these deep learning-based methods, they're really powerful, as you see, for MRI imaging. They can also really drive technology forward in other ways. So this is a paper from a group in Hong Kong, which is very impressive because they basically use very similar ideas to enable you to build a very low field MR scanner. So you use very cheap components, very weak magnetic fields, for example, without active shielding, and use AI to drive the reconstruction of this very poor quality data which you can collect. And you see some images from their science paper which show that this still produces very interesting looking images from a piece of hardware which is probably $30,000, $40,000 rather than $2 or $3 million. So there's a lot of potential in this. You can also apply these ideas to other modalities like ultrasound, or for example to try in CT imaging. The problem is not so much that you want to reduce scan times, you want to probably reduce those, but the same ideas, collecting less data and using AI to reconstruct, they can help you in those scenarios as well. Now I want to switch a bit gear and sort of show you some other applications a bit higher in this pyramid, which I showed in the beginning. I think you all are familiar, or believe me probably, that there are lots of good algorithms for segmenting anatomy in the heart, the whole body images in the brain. There are lots of really good algorithms out there. And there are also now more and more large-scale data sets which you can apply these algorithms to. One of these data sets which we work quite a lot with is the UK Biobank, which is a very nice study because they are sort of collecting whole body MRI images, brain MRI images, cardiovascular MRI images from over 100,000 subjects. And they're doing this even now longitudinally. That means they actually have for every subject, they're starting to get multiple time points. In addition, what they have is they have 500,000 subjects which have genetic testing, which have lifestyle, physical activity measurements, and also linked to healthcare outcome data. So this is an incredibly rich data set which is available to researchers worldwide. Now, one of the things you can do with that is you can, for example, use these segmentation algorithms to analyze this vast number of images. So we started off doing this a while ago by, for example, using automated segmentation of all these data sets to try to get reference values for example, cardiovascular phenotypes, which are based on sex as well as on age. So you, for example, see here different cardiovascular parameters normalized for age in this particular case. But one of the other things you can do is you can also test for associations or correlations between these phenotypes you can derive from imaging and all these other measurements you have in UK Biobank. So for example, here we compare all the cardiovascular parameters to all the lifestyle, physical activity, cognitive scores, other measurements in UK Biobank. And you can, for example, see here that there are very strong correlations or associations, I should say, that this is purely based on correlation. This is not causality in any way or form, but you can find very interesting correlations and you can study them further by taking the image data, completely automatically analyzing it, and then correlating it with all the other information you have. I also mentioned that you have in UK Biobank outcome data. So one of the things which we've studied more recently, this is a paper currently in press in digital medicine, to try to predict risk scores based on a baseline scan of the anatomy of, for example, whole body imaging and cardiovascular imaging for particular types of diseases. And what we looked at, and I apologize that this is a bit sort of low resolution here, we sort of looked at, for example, ICD codes for cardiovascular disease, pancreatic disease, liver disease, and others. And basically, because you have so many subjects in UK Biobank, you can basically have a population which doesn't have the disease, and you can sort of age and sex match it to patients who get that disease after a while. And you can try to see whether you can derive, based on the imaging information, a prediction result which would highlight whether a subject will get within a certain time scan these diseases. And we've done, and again, I apologize for the low resolution here. You get very interesting results that actually quite expected. For example, if you want to predict cardiovascular risk, the MRI images of the heart are the most useful ones. The whole body images tell you quite a lot of metabolic disease and other things. So there's a lot of quite interesting but also not so surprising findings. But you can actually do a very good job at risk prediction using this type of data. So what I wanted to do also is give you a bit of an overview of whether it's possible, and I think we've already seen quite a lot of talks on this, to build AI models which serve multiple purposes. And of course, quite often this is called a foundation model, and there are lots of different foundation models around there, and they can be applied to lots of different applications. And I think also in our community, we start to build more and more of these models. And I wanted to show you one particular example of this, where we try to build such a unified model, for example, of cardiac MRI, taking lots of different cardiac MRI as input. For example, cardiac MRI is often acquired in different orientations. You can have different scan protocols, perfusion, cine imaging, and so on. But also then build a model which can actually solve a lot of different downstream tasks. So here in this particular case, for example, solve segmentation tasks, do motion tracking, but also predict, for example, phenotypes from the images directly. And the approach which I wanted to briefly show you is something which one of our PhD students showed last year at MICI, which basically first does a representation learning approach to learn a representation of all this imaging data, and then effectively train different decoder models for different downstream tasks. So the actual representation learning uses something which I think many of you will be familiar with. It's a mask image modeling approach where basically you train a transformer-based model where you effectively hide some of the tokens, input tokens, and the model is trained to reconstruct the correct output tokens for these missing tokens. And if you use, for example, the UK Biobank data, you have quite a lot of data in this available. And so this is, of course, completely unsupervised. So it's agnostic to the downstream task. But once you have sort of trained that model, you learn that representation, and you can now try to learn very simple decoders, for example, very simple linear layers or so, which, for example, predict phenotypes, or which predict, for example, segmentation labels from that data. And I just wanted to show you that if you, for example, look at certain phenotypes of the images, you can already see that the representation you have learned really starts to encode these phenotypes. So here we just color code the latent space representation, and we have to reduce it to two dimensions because I can't show anything else on this slide. But you see, for example, if I, for example, take parameters like left ventricular mass or stroke volume or end-systolic volume, there's a very clear arrangement of the data in the latent space where basically the representation already encodes quite a lot of that information. So it's very easy to train a decoder which predicts these phenotypes. But you can also use that representation to then effectively have a simple decoder layer which, for example, then performs segmentation of this. And what you see here is sort of a comparison of different segmentation methods, where the ones which we have sort of developed is just using a very simple decoding layer to actually get to the final segmentation. Now, I think if you sort of think about such a representation, you can probably also enrich it with other information, correct? And this is what I wanted to show you in the last example here, is where if you, for example, take MRI imaging to investigate the heart, it's of course a great modality, but it's expensive, it has limited availability, and of course the first line of defense is probably actually you doing an ECG of the patient before you actually go to do something more complicated, correct? But of course an ECG tells you much less information than a cardiac MR. But it's also much, much cheaper, correct? And it's much more widely available. So one of the things you can sort of think about is, well, could we actually try to predict a lot of these parameters I've shown you, perhaps even from the ECG, by doing this in a clever way? And we have sort of played around with that a bit, and what you see here is sort of an approach where, let's assume I only have the ECGs. What I could do with the ECGs, I could do the same pre-training approach to build a sort of foundation model of ECG data, which I've used for the imaging. So, for example, I take my 12-lead ECGs, I encode it into tokens, and then I basically have a masked modeling approach where I effectively hide some of these tokens and force a network to predict these tokens. And then I'm basically solving a reconstruction task, and I'm minimizing the mean squared error between my reconstruction and the true signal. And that's very good to training a good model for ECG alone. But what we can also do, if we have matched MR images for all these patients, like for example in UK Biobank, I can also add a contrastive learning component to that using something, for example, like CLIP, where I basically say, I want my representation derived from the ECG to match my representation derived from the MRI imaging. So this is a very sort of straightforward contrastive learning approach using something like CLIP, where you can very simply enforce those two representations to be very similar in your representation space. And if you do that, then once, of course, you go to the inference stage, you can sort of see, well, how much can I now predict from the ECG, because the representation it has learned is enriched with information from the MR imaging. So can I use it for disease classification? And do I get better disease classification results? Or can I even predict from the ECG some phenotypes about the heart which you can normally not see in the ECG, or at least humans would find it difficult to do that. So you can, for example, do a fairly good regression of some simple cardiovascular parameters like size of the chambers, stroke volume, and so on. You get a reasonable regression. And you can also show that if you have that representation, that joint representation, you get a better disease classification compared to a disease classification which is only derived from ECG, from an only ECG trained model. So you can see that there's quite a lot of potential for also integrating different modalities in these foundation models. Now, I've shown you hopefully quite a lot of interesting examples of where AI seems to work, but I also wanted to highlight some areas where we all struggle with AI, and quite often we struggle because we don't have enough data. The first example is perhaps something you're all very familiar with. I'm, by the way, very happy that the audience to this talk doesn't look like the audience on this slide. Of course, it looks much more diverse, and that's very good. And we've also seen that a lack of data can quite often mean that we have much more problems with biases and fairness. And actually, this paper by Ziad Obermeyer, for example, shows this also very nicely in the context of a healthcare system. Not only, this is not an AI-related problem, this is a problem we have had in medicine for many, many years. But quite often the problem is really amplified because we don't have enough data. We also have a huge amount of variability. So I always tell my own PhD students when they effectively have trained a model on a lot of data like UK Biobank. So this is, for example, a very nice representation of UK Biobank. It's 100,000 subjects, but they're all mostly healthy at the time of imaging, correct? And now if they go to our radiology department and they apply it to data which looks like this, it's not so surprising that this doesn't really work, correct? So because the two distributions don't really match. So, and of course, there's not only a pathology as a reason for that. If you have different scanner manufacturers, they not only produce scanners in different colors, but they also produce scanners which generate images which look different. We can do lots of different imaging sequences and so on. So there's a huge amount of variability. So ultimately, it'd be great to have as much data as possible. And actually, this article in the Financial Times, a UK newspaper, they basically advocate for making all the NHS data available for building AI models for predicting disease. And of course, in principle, that's a great idea, correct? Everybody would say, let's do that, but please don't use my own data for this, correct? So one of the things which we have sort of started to look a bit into over the last couple of years is how do we deal with privacy in building AI models? And how do we ensure privacy? And I also wanted to point out, this is from one of my postdocs, a very nice review he wrote a couple of years ago. So there are lots of different methods in this paper which are outlined in this. But we all know there are a couple of different techniques which we can use to help us with this. One is federated learning, correct? I think you're all familiar with this. I've seen already there are a couple of posters, really nice posters on this. And the idea is very simple. You basically send your AI models to where the data is. you train locally, you aggregate the results, and then you're sort of iterating across this. And that really helps you with solving some data governance issues. But also, this is something which we looked into, and I will show you an example of this. Federated learning in itself doesn't really help you with privacy. And hopefully I'll show you in a moment why it doesn't really help you with privacy. But it helps you with data governance because you know where the data is, correct? So if you sort of go more into the CS community, it's quite well known that there are lots of possible attacks on AI models, correct? I've listed some of them. Some of them are not privacy related, like model poisoning or backdoor attacks. They're not really something which probably plays a big role in medicine. But for example, membership inference attack, where you can infer whether your data was used in a particular AI model, might be quite sensitive. Or perhaps this model inversion attack, which I want to show you on this slide. So let's assume you build a big AI model, and you're doing it with federated learning. And you have an attacker who can see actually the gradients you're exchanging between the central site and the local training site. What they can do without much effort, they take a big AI model, you can invert that model to regenerate the training data which was used to generate that. And if you look at these images, you might say, well, that's a pretty bad reconstruction, looks very blurry. But actually, most people can infer some sensitive information from this. For example, you see a patient on the top left had a mastectomy, patient at the bottom left has implants. So you can infer quite a lot of sensitive information even from that. So how can you avoid that? And I wanted to show you one particular way of avoiding that, but you also heard the last talk in the previous session was about synthetic data generation to avoid that. That's also a method. But you can actually use something which I think is a quite clever idea. It's called differential privacy. And because I don't know whether all of you are familiar with differential privacy, I just want to give you a reasonably topical example of what differential privacy means. And it involves a lot of coin flips. So just bear with me for 1 second. And the example is, I've chose to base it on the last presidential election here in the US. And so now I could sort of ask all of you, I know some of you could have probably not voted in that election, but who you have voted for. And I can sort of see that you might be hesitant to give me an answer, no matter which way you voted, here publicly, correct? So let's assume we have a very simple protocol. And the protocol basically assumes that all of you throw a coin in private. So you all flip a coin, you don't tell anybody else what the result of the coin flip is. But we have the following convention. If it comes up head first, you answer truthfully, you tell me who you voted for. And if it comes tails up first, you take the coin again, you flip it again, and you give me a result based on that second coin flip. So it might be heads if you say Kamala Harris, and tail if you say you have to say Donald Trump, correct? So now let's assume I would ask Ron here in the first row, who have you voted for? And he would tell me Donald Trump, and then I might say, "How could you?" And then he might say, depending on, he might say, "Look, actually, it was a coin flip which forced me to give you that as an answer, because the answer has two components. It has a truthful component, and then it has a pure noise component, right? And that pure noise, depending on how fair these coins are, you can control how much noise there is. So somebody like Ron has always plausible deniability. He can always say, well, it was actually the coins which forced me to do this. Now you might actually say, okay, and actually this is what we observe, correct? It's a mixture out of the true signal and the coin flips. Now why do I tell you all of this? Because of course there's a connection to how you can use this in imaging. And most of you will be very familiar with a standard stochastic gradient descent algorithm, which I guess is a bread and butter of every deep learning algorithm. It's on the right-hand side. if I wanted to add differential privacy, this plausible deniability to it, I basically modified 2 lines of code in that stochastic gradient descent. And those lines of code do 2 things. The first one clips the gradient, so there's a limit to how much any sample can influence the gradient. And the second component adds noise to it. This is what you have seen on the previous slide. Okay? So if you now train an AI model doing that, what you get out, if you attack the model with the best possible effort, you get out something which looks like this. And so that's, of course, very encouraging, because now you can no longer reconstruct anything. And moreover, you have mathematical guarantees that this will be the case. It's not just, you have to believe me, you can actually show that there are mathematical guarantees for that prediction. Now, you probably all ask me, so why does not everybody do this all the time? Because that seems to be a no-brainer. It's easy to implement. Why not do it all the time? And the reason why you don't do it all the time is because there's, of course, a performance trade-off involved in this, because you're adding noise. It will take longer to converge for your algorithm. And sort of we looked at, can we actually find the right noise level so that you add the right amount of noise, that you get privacy protection, but still the same performance as before? Turns out, yeah, you can do that. Again, sort of apologies for the low resolution picture here, but effectively you can find a good trade-off between privacy and performance. So I think there's a good reason you can actually use differential privacy in a lot of practical scenarios, but you have to think a bit carefully about how much privacy you really want, because that influences how much noise you add, and that also influences performance. So in the last 5 minutes, if that's okay, time-wise, Ron, I want to show you a few sort of examples of what I think might be next. And I want to show you that based on, again, some newspaper headlines. You probably have seen these headlines where it's basically shown that LLMs are very good at many clinical questions. In particular, if you evaluate them on, for example, US medical licensing exams, turns out that even old versions of ChatGPT will pass that exam better than humans. And if you sort of look at the state of the art, I think the passing threshold, if I'm not correct, is actually not that high. It's, I think, 60%. Even older models like GPT 3.5 can do that relatively well. And if you look at more recent models, they're way better than that, and they pass this US medical licensing exam with over 90% accuracy. Now, the question is, does this tell you a lot about performance in the real world? And I would argue probably not, because if you actually look at what the medical licensing exam does, so it has different components. First one, of course, it's based on multiple choice, correct? And that's not a real world scenario. The second one is it gives you all the information you need for diagnosis upfront. And the final one is sort of, they tend to focus on the classical symptoms, for example, for diagnostic tasks. Right? They don't give you borderline cases. They give you very clear cases where there's a very clear answer for. So actually, this is probably not a very good proxy. So it doesn't really reflect what happens in real-world settings. So one of the things we did last year, we tried to develop a benchmark for actually how you evaluate LLMs in a real clinical scenario. And that's also based on testing how well the LLM can actually perform in gathering the information. Because if you're in an emergency room physicians, the patient comes and says, I have abdominal pain. They don't come with an image and all their lab measurements. You have to figure out what to do. And you also have to order the right test, right? You can't order a CT just because you feel a CT would be nice to have. You have to have an indication for it. And one of the conclusions, I don't want to show you all the things, but we found actually almost all of the LLMs which you can nowadays test, they all struggle with really following clinical instructions. They don't follow clinical guidelines, even if you prompt them with the guidelines. And they often have problems interpreting lab results, because these lab results are quite often numerical results, so they struggle with quantitative information. And they're, for example, not invariant to the order of information. So if I, for example, tell you a patient has diabetes and high blood pressure, I get a different result than if I tell you the patient has high blood pressure and diabetes, which of course gives you exactly the same amount of information, correct? So there's still quite a lot to be done, I think, on these language models, and you see almost every 2 or 3 weeks a paper in a high-impact journal coming out which tries to address some of these things. So I think there's a lot of interesting work out there on this. I want to just finish off by giving you one example where we sort of also try to go a bit in this direction by effectively comparing or building vision language models, so models which understand imaging but also understand text. And in particular, we have focused on an application in OCT imaging of the eye for ophthalmology. And this is a paper which is now accepted in NPJ Digital Medicine. And it's basically trying to have an algorithm for automatically constructing such a model. And what we did in this particular case, because we didn't want to ask ophthalmologists to annotate thousands and thousands of images, we actually took a database of images for which we have automated measurements. So we have automated measurements of retinal layer thickness, of pathologies and so on. And then we use the language models to take these measurements and convert them into text. So we artificially generate question and answer pairs for these images. And we use them to train a vision language model for that. And in the second stage, we also ask an ophthalmologist or several ophthalmologists to write very detailed reports, but only for a small number of images. And then again, we used an LLM to generate question and answer pairs from this. And with that, you end up with a model which actually, again, sorry, apologies for the low resolution. I think this comes because it's transferred to another computer. But you can basically ask questions saying, describe what you see in the image, or write a referral letter for a patient where the following diagnostic guidelines are given. And you get a very reasonable text outputs. We compared it to expert ophthalmologists, and these models are not much worse than these experts. You can also do things where you highlight certain bits in the answer, and then it will show you where these features are present in the image, so you can also get some degree of explainability in these vision language models as well. So hopefully I've shown you lots of exciting things which I think you can do with these language models, and I think I'm suspecting that, for example, next MIDL or next MICI, there will be lots of papers on this as well. I just wanted to finish with one thought, and that's, I think what of course might happen next is, I think one thing you have seen at the end of last year, quite a lot of Nobel Prizes for people who have either developed AI algorithms or who have revolutionized a field like chemistry by applying AI algorithms. So perhaps there will be in the future also the Nobel Prize of Physiology to people who use perhaps AI to help interpret medical data or understand diseases better. So I think AI is likely to become a tool which I think every clinician will use in their daily practice, whether they do it implicitly or whether they do it explicitly. And with that, I want to finish. I want to acknowledge all the people in our group who present or who have done many of the papers which I showed you here today. And also, of course, all the funders, which are very important, because without their money, we couldn't do what I've shown you today. And I would be very happy to answer any questions you have. Thank you very much for your attention.
Okay, terrific. Any questions? Please go ahead.
So thank you so much for your talk. So in order for AI to have an impact in the clinics, we as researchers don't just have to develop good models that actually improve, but we also heavily rely on the vendors to adopt this technology. And because you mentioned MRI, I mean, the MR vendors are notoriously slow in adopting. It took maybe a decade for compressed sensing to reach the clinics. How do you see the willingness of the big vendors to actually adopt this technology? Because the bar for AI, I guess, is much higher than for compressed sensing, for example.
I completely agree with your assessment. So I do think that most vendors are not super enthusiastic about this. I think we have seen that compressed sensing, as you're saying, probably took 10 years, even longer perhaps, to get into a product. I think you have seen some of the AI algorithms more recently. They took much less time to get into a product. And partly also because, for example, other companies, for example, United Imaging also, they have just started doing it, and then some of the other vendors will do it easy. So I think there's one element, if there's pressure from the users for this, I think that definitely helps. I think in radiology, we have always had the problem that the big vendors, but also startups, they all struggle with figuring out a business model of how to make money with AI in radiology. Unfortunately, I don't really have the sort of silver bullet for that, but I do think we have to effectively get people like Ron and the users of that technology to be so enthusiastic that they basically say, either we're willing to pay for it, or we pressure the manufacturers or the vendors to actually provide it, and if you don't provide it, you're not competitive. That's the only thing I can sort of say to that, but I don't know the magic bullet for this.
Thanks for the really great talk. I have a more technical question about an accelerated MRI reconstruction. Do you think it's theoretically possible in the future to do this in an active sampling kind of sense, so that you can in real time process the information that you still need to gather from the case space?
I think you, in principle, could do that. I think this will probably make the technology more sort of less automated. I have the impression that there's more parameters you have to figure out. Have you really collected enough? And so I know people have, for example, tried to optimize the sampling pattern. I think that gives you very little benefit overall compared to. I think basically when you say active, I think what probably could make sense is to say, okay, I've collected enough information, correct? I stop the scan because I'm doing online reconstruction and I see when I've collected enough information. I'm not sure whether you make that the problem of doing, for example, getting into a clinical product more complicated by doing that. I think from a scientific point of view, it certainly makes sense to try to do it online and have some criteria to figure out what you want to do. I think it also, there are some people now basically trying to use previous scans to help you with accelerating the next scan. I think that is probably, in my mind, a better technology or better sort of route for doing this.
Okay, thank you.
So yeah, thank you for a very stimulating talk. My question is really related to your last section, which is the quality of the data that you used in the ophthalmology project. So you mentioned, if I understood correctly, that you actually had ophthalmologists generate new data related to the images that you showed them. Normally, we don't have that luxury. And I was wondering, so we have, radiology reports, perhaps, or maybe we even have crowdsourced data from the internet about some radiology images. So I'm wondering if you could give us a perspective, how important it is to have this very high quality data that you used.
So I think it is quite important. So in the example I showed you, for example, we try to minimize how many images the ophthalmologists have to annotate. And we settled on, I think we had 330 images. So it's a relatively small number of images. And then the large or the vast amount of the images, the annotations were generated automatically because we had, for example, the measurements This is from a clinical lab which does pharma studies where they have quality controlled the automated measurements. So I do think that clearly there's a very, very strong correlation between how good your model is and the quality of your data. And I think crowdsourcing, for example, in the case of radiology, I'd be quite skeptical whether you get good enough quality data. So what we, for example, try to do is we try to use structured reporting where, for example, in radiology, the radiologists are forced to use a structured template according to which they have to report to generate that high quality data. But I should say that most radiologists hate, or I've experienced with hate doing that because it really limits what they can write and they're not very keen on it. But in a lot of clinical trials, they have to do that anyway, correct? So because the clinical trial requires that.
First of all, thank you so much for a very interesting and stimulating presentation. My question is a little bit different from what you presented, but I still wanted to get your opinion. Obviously, we've all heard about the rhetoric of agentic AI, and I wanted to get your opinion on how like agentic AI can get implemented in medical imaging, especially in like the sort of image enhancement realm, and like how like an AI will have to do like the sort of quality control and reliability checks.
Okay, so I completely agree that agentic AI is the hot topic. Also, I think in medicine or in medical imaging, I don't know, you probably have seen this paper voxel prompt, which, for example, is I think from Adrian Dalker's group, where they, for example, have a system which is a bit perhaps sort of going in the direction of these vision language models where you can basically say, look, segment the following structure for me, and the model will figure out what is the best tool and involve, for example, an agent which actually does, for example, segmentation of a certain structure and so on. So I do think there's a lot of potential in this. I think it requires you to have, though, agents which are very good at performing individual tasks. So I think we struggle perhaps with a problem that we have lots of tools out there, but for example, they're often not validated, they're not FDA approved or so. Perhaps that would be if you have, for example, an agent which actually you can rely on the output and you know the output is true, then I think you can sort of, if you can verify these agents with respect to some specification, I think then it becomes very interesting on what you can do with agentic AI. At the moment, I haven't quite decided whether this is just hype or whether there's really something very interesting in it. But it certainly has a lot of interesting ideas.
Thank you.
Hi. I wanted to ask you about, you were giving the little talk about differential privacy. I wanted to ask you about, so in like this area of research that we're doing, like I feel like a big part of what we're interested at the end of the day is being able to bring our developments to the clinic and have like clinicians like be able to trust the work and be able to like actually use it. And so there is this like big trade-off between all these different things, between like DP, between like interpretability, and between like fairness. And so these are all three like important concepts that are important like in isolation, but they're also kind of sort of exist like in this like trade-off space where like you kind of have to like weight them at different degrees to be able to do anything because they like they detract from each other. So I guess my question is, in order to sort of prioritize our goal, which at the end of the day is to like help clinicians, what does that balance sort of look like between these concepts? And like, should we really be focusing on privacy at this point if like clinicians can't even trust like that our models are doing what we say that they do?
I think that's a very good question. And I think my answer would say there's probably not one universal solution, and it might depend on, for example, your local environment. So for example, one of the reasons why we started all this work on privacy is when I worked for a long time in the UK, and then I moved to Germany, where the privacy regulation or privacy is taken very, very seriously, and people are very worried about this. And so there, for example, there's, I think, a different preference threshold between how much weight you put on privacy versus other things, correct? And I know, for example, in the US, probably there's a different attitude to that, and there might be a different optimal operating point. That's what I'm trying to say, is there might not always be the same point. You might, for example, say in China, in the US, in Germany, you all use different preferences. I think one of the things which I think is important for us as researchers is to understand that we can actually trade off, or that there is a trade-off between these different things, and then you might be able to optimize this operating point, where no matter where you actually decide what your objective function for that is. So I do think that's very important, and I think for me the biggest important factor was having a discussion with, for example, in our university hospital, with our, for example, the data protection officer, with the clinicians, but also with the patients, because, for example, privacy is a classic example. If I ask most of you, are you concerned about your healthcare data being private? Most of you would probably say yes. If you talk to a sick patient in the hospital, they say, actually, I don't care. I want you to make me better, correct? My preferences are completely different to what perhaps the general population has. And I think you can only figure that out, I think, by talking to your local collaborators and figuring out what they really want. And then I think it's our task to make it happen in some sense.
That makes sense. Thank you.
Okay, one last question.
Thank you for the great talk. I'm really impressed by the ECG MR correlation project. Just a practical question. So we know that ECG get distorted in the MR scanner. How is that handled, and especially for like even patients with arrhythmia?
So actually, this data is collected as part of UK Biobank. It's collected outside the MR scanner. So the ECG in the MR scanner is only used for triggering for the image acquisition. It's not used for a diagnostic purpose. But all of the patients in UK Biobank, they have on the same day, before they go to the imaging, they have a 12-lead ECG exam. So we use data which is sort of, it doesn't come from inside the scanner, because that you couldn't probably use.
Thank you.
Okay, let's thank our speaker.
to the gene activities. But the size itself is not just about seeing more pixels. Each bean also belongs to a larger structure, like spot or a tissue region. So for each bean, we extract pictures at 3 different levels: bean level, spot level, and region levels. These multi-skew inputs allow the model to learn both fine and coarse grained vision informations. We then pass each patch through an encoder to get the image features and use a cross-attention mechanism to fuse the information across different levels. After fusion, we concreted these features from different levels and giving the model a more rich multi-skew representation for each bean. To go one further step, we also want the model to understand the spatial relationship between the nearby beans. So we construct a graph based on how close the beans are to each other in the tissues. Then we feed this into a GAT transformer block, which allows each model to aggregate information from its spatial neighbors. This helps the model to capture the local coordination patterns in gene expressions. A transformer layer is used to adaptively aggregate from the neighbor information and then enhance the representation of the features. Finally, a regression head will generate the gene expression predictions for each level separately. To supervise the model effectively, we design a hybrid loss function that balances accuracy and consistency across different resolution levels. We first apply a prediction loss at bean level, spot level, and region levels. We use both MSE and the PCC loss to capture the accuracy as well as the gene expression trends. For the spot level and region level, we only use the correlation loss to avoid the over-penalizing the cost level predictions. Secondly, we add a consistent loss, which encourages the model to produce similar prediction across different skews. For example, if a bean prediction looks very differently from their corresponding spots or regions, the model will get penalized. Together, these two components help the model not only to make accurate prediction at each level, but also maintain the coherence between them. To evaluate our model's performance, we use 2 different datasets to see its performance. It includes one provide dataset called VUMC kidney dataset and one public dataset called CRC dataset. The VUMC data includes 12 HD samples with 3 different resolution levels, and the CRC dataset contains 4 samples including 2 tumor and 2 normal tissues. We performed a 4-fold cross-validation at whole WSI levels. For pre-processing, we randomly sample 6,000 beans per slide and extract 112 times 112 image pictures, centered at 8 micrometer and 6 micrometer beans. At spot level and regional levels, we also crop larger pictures and aggregate their gene expressions from each beans. To build a meaningful multi-resolution input, the paired pictures across different levels were matched based on their spatial distance. And finally, following the strategy introduced in STNet, we select the top 250 genes with the highest average gene expression from the 20,000 candidates for our prediction targets. We benchmarked the magnet against several SOTA baselines across these 2 datasets, and as is shown in the quantitative labels, magnet consistently achieves the best performance across all the resolution levels, and also they outperform in the more challenged high-resolution levels settings. And the visual comparison on the right highlights the superiority of magnets in predicting the gene expression maps. Compared with existing method, magnets produce outputs that more closely resemble the ground truth, with significantly lower MSE values for pivot genes. We conduct an ablation study to understand how each part of our model contribute to the performance. As shown in the results, adding the GAT transformer blocks and incorporating multi-resolution features clearly improves the model's accuracy, especially in the high-resolution levels, where the original gene patches contains very limited information. We also find that using a consistent loss also helps align predictions across different SKUs, leading a better learning of high-resolution features. In addition, we tried replacing the ResNet 15s with the Uni foundation model, which is tailored for pathology images. However, performance slightly dropped. This is mainly because the Uni is a much larger model and it forced us to use smaller batch size during the graph training process, which limited how much neighborhood information the model could access. So in that setting, a lighter backbone like ResNet 50 actually worked better. To summarize, our proposed framework magnet integrates cross-attention layers and the GAT transformer blocks to effectively extract and fuse multi-SKU, multi-source features. This architecture is specifically designed for tackle the information bottleneck that arises when predicting the high-resolution gene expression from small, high-resolution images. Beyond the model design, we've made a magnet open source tool and conducted a detailed benchmark study on both a private collected dataset and a public dataset. We hope this work could not only set in a strong baseline, but also can inspire the future researchers in high-resolution spatial transcriptomics. Finally, I'd like to thank all of our collaborators and everyone who supports this work. And thank you for your listening. I'm happy to take any questions.
Thank you very much for your talk. We have time for some questions. Yes, please.
Hi, great work. I know spatial transformics usually have this large sparsity issue. Do you need to do some spatial smoothing for this HD data as well?
Yeah, it's a great question, and we also find a phenomenon that in HD data, the gene expression is extremely sparse, and most expressions are just like zeros. So in this work, we only select the top expression genes to make the predictions, and to ensure the sparsity will not affect the model's performance. And we also, in the evaluation part, we also find the PCC might not be a useful metrics in evaluation for the spatial relationship between the prediction and the ground truth. So in this work, we, instead of using PCC to represent the spatial correlation, we use it to represent the relative correlation within the patch, within the spots. Yeah.
Thank you.
Any further questions? We have time for more questions. And probably I have a question. So I'm not the main expert here for spatial transcriptomics, but in these studies, I always wonder, this is relatively few samples, right? So individual WSIs. Yeah. You have lots of patches, but only a few samples. Perhaps could you comment a little bit on observations regarding risks of sample level overfitting, color variation, domain kind of robustness of such methods, especially yours?
Yeah, it's a great question. It's so here, what you mentioned is a good question in spatial transcriptomic settings. Since in ST data there is a thing we call the batch effect, and how the data generated will definitely affect the model's performance. While in our work, our aim is not to address this issue. What we want to do is to introduce a good method to predict the models. And our researchers focus on the data-specific settings, and we train different weights for different data settings. And yeah, it's a great question, and it's also required a lot of time and effort to solve these issues. And thank you for your question.
Okay, then thank you very much for your talk. Is another question, please go ahead. We have time for one quick question.
Very interesting. So I was wondering, a lot of cells have very specific cell lineage specific gene expression. So have you considered taking, helping you with the cell morphology, where you have, on the H&E you can do a segmentation and classification, to see what cell you have, and then combine that with the gene expression?
Yeah, it's a great question, and I think it's what we can do in the futures. Yeah, when we combine the cell types as well as the morphology information, and we use this specific information to get better representation to predict or to get the prediction for the ST data. It could be a very, very helpful ways, since we already have the previous knowledge about the image feature type about the cell types, and it definitely will improve the performance in the gene expression, since the model can understand which the cell belongs to or which this part belongs to, and it can make more specific predictions and make a more accurate understand about what this areas belongs to, and to get better performance. Yeah, thank you.
Okay, then let's thank the speaker again.
Thank you, our first speaker, and then we welcome a second speaker from University of Paris, Italy. So this topic will talk about decoupled asymmetric fusion of tabular and echocardiographic data for cardiac hypertension diagnosis. Welcome.
Okay, so hello everyone, and thank you for being here. I am about to present my work about asymmetric fusion of tabular and echocardiographic data in order to perform clinical diagnosis. So I am a PhD student at Sorbonne University, and I work with Nicolas Thome and Olivier Bernard also at Creatis inside Lyon. So first, let me introduce the problem I will handle with this work is about characterization of cardiac hypertension. And to do that, we use two modalities, which is time series features that are automatically extracted from echocardiography videos. And also, we use tabular data, which will be very important in our work. And it is what we call electronic health records. And so our main contribution in this work is to handle a classification problem to diagnose hypertension of heart disease. And to do that, we perform multimodal fusion with asymmetric modalities. So what are asymmetric modalities? We can, in a way, determine what when the two modalities are not of equal importance. When you perform, for instance, unimodal learning on one modality or in the other, with the other, you can see with this mini score table here in the slide that when we learn only on tabular data, the area under the ROC curve is much more important, higher than when we learn only on time series, for instance. And that can be explained with the data. I will get to this point later. But first, secondly, you have to also notice that these two modalities can be very heterogeneous, meaning that tables and time series can be very, very different in that way that if you just simply concatenate them with MLP network, for instance, or with XGBoost, you downgrade basically the performance, because it is as if you had some noises to the most important modality, which is the tabular data. So we have to think about a more sophisticated way to fuse these two modalities. So naive fusion strategy does not work and underperform state-of-the-art models. So one solution that we propose in our work to the asymmetric and our fusion problem is that to consider the two modalities as one modality, the tabular data, as a primary modality, which will be treated by the model as the main core information, and one secondary modality, which is here the time series, which will be treated as a contextual refinement by our model. So let me speak about a bit the related works that inspired a lot of works. What is very important to know is that for tabular data prediction and tabular data encoding, tree-based models are still nowadays very dominant, the very dominant approach. Maybe you heard about XGBoost. For instance, there is also other models that use tabular data, a lot of tree-based models, but they are still very dominant in a sense that deep learning does not reach in every setup the score that tabular model, tree-based model reached. But the problem is, like I say, they have been tailored for tabular data specifically. And so when you want to add another modality, it doesn't fit very well and it can underperform without using the information that can be brought by another modality. So that is why we also consider the transformer-based model. We can also fit tabular data very well. For instance, there is maybe a very, one of the best transformer models that exists for tackling and encoding tabular data, which is the FT transformer, also known as feature tokenizer transformer, which tokenize categorical data and numerical data in a different way, which can be very practical to use every column of the tabular data as tokens. And then with cross-attention, for instance, or self-attention and concatenation, you can perform multimodal fusion, which is better than simple naive concatenation. And finally, we also need the framework of the contrastive-based models because it can, in a way, improve the results in when you want to fuse after aligning. But the problem is that aligning can only theoretically handle the redundancy between the two modalities. And so we have to think over the problem in order to also take into account the specificities of each modalities. So it is our models with two main contributions. In the middle, you can see that we have the decoupling module that separates the primary modality, which is here the tabular data, into shared information with the other modalities, meaning that in the tabular data, for instance, we have also values that are directly or indirectly extracted from the echographics. And so this is the information of tabular data that is shared with time series. And also the other token, which is the tabular specific modality, like demographics, for instance, or biological information, like age, weight and height, for instance, of the patients. We cannot retrieve this information in time series. And so after decoupling the data, we fed the tokens into a transformer, a kind of transformer, which use cross and self-attention in an interleaved way that considers so the tabular specific modalities as the main core information and the time series with the shared information as the contextual refinement. I will give you further details after that. So maybe the most important part of our work, I will try to get a bit simple to get quick and fast here, but if you have further questions, you can ask me with my poster if you are interested. So the decoupling module is based on two contrastive losses. The one that is the shared specific decoupling loss that pushing away the tabular specific information far from the time series information and getting the tabular shared information close to the time series. It is a triplet loss, basically, with a bit some modifications. And we also need a regularization loss because we cannot just push away the tabular specific information, otherwise it will be a trivial point. And so we had some label information has in the supervised contrastive learning environment with also specific losses that enable to tackle the tabular specific information before fusion. And so now the asymmetric fusion scheme, which is quite simple, it's just a transformer with self-in cross-attention modules. When you take the main information in orange here, like the tabular specific information as the main core information, and you use cross-attention to perform the multimodal fusion at two levels of these transformers. So basically the shared information as a time series only is used here for the contextual refinement. That's how we do the asymmetric fusion scheme. And yes, we use a CLS token as in BERT, for instance, that we extract from the time series, from the tabular specific tokens, which is a tokens that have been made especially to represent the patient in the latent space. We feed it into a prediction head to perform classification, classical, with cross entropy, etc. So about the dataset we use, it's a valuable dataset with not so many samples, but good quality dataset with 239 time series tabular pairs with 13 tabular features and 14 time series features. And the 3 target classes we want to predict here is quite important because this is ordinal. They can be classified like an ordinal classification. It is 3 degrees of disease of the cardiac disease of patients. First, we have white coat hypertension, meaning that the patient is not sick, but he presents symptoms when he gets to the doctor because he's stressed. So this is a healthy subject. Also, we have the control and uncontrolled patient. Both of them are sick, but one of the ones who are controlled, we can control their disease with medication, and the ones who are uncontrolled, they are very sick, and unfortunately, it is not possible to control them with medication. This is important because the difference is subtle between control and control, and using time series only does not enable us to make the difference between patients which are controlled and control. That's why when you train only a feature tokenized transformers on time series, you cannot improve very best compared to the random, for instance. But you can fuse this modality with our DAFT scheme, and you see that we outperform state-of-the-art multimodal fusion models like MLP, contrastive learning, IRIN, and also the FT transformer without decoupling. And you can see with the ablation studies that both the decoupling module and the asymmetric fusion scheme are important to get to the best results we can have with that. Some qualitative analysis before finishing. So you can see also that in the latent space represented by the tokens who are shared, the tokens who are specific to the tabular data and time series token, you can see that with the pack map embedding, we can separate in the latent space the information, and it becomes clear that the specific tabular data of the main information is a bit pushed away, which can enable better fusion when we get to the transformer for asymmetric fusion. And so to conclude, so let me summarize. We have a main contribution, which is a new fusion strategy based on an asymmetric scheme thanks to a decoupling module. The decoupling module separates what is considered as the main information as information in common with the other modalities, which is redundant in a certain way, and information which is specific to the tabular modality only. And so the fusion scheme represented that fuse the both modalities. And so as you can see, it's improved the results compared to other state-of-the-art models. So I will be happy to answer to your question if you have.
Thank you. And any question from the audience?
Hello, great talk, thank you. As I understand correctly, you use the tabular data for the key, for attention, you use tabular data as a...
As a tabular data, specific is a query, and the key value is tabular shared concatenated with time series.
Okay, so you use the shared information as a key, and then you use the tabular data as a query.
Yes.
And the value is also the tabular data.
Yes, the key is the value is the same.
Did you try the other way around?
Yes.
And
it does not perform. It underperform. We have some explanation because query in the transformers like this is have more parameters in the transformer. The query is more important in a way because it has the same shape before and after the transformer. So the main modality have to be assigned to the query. And if we do the contrary, you will see that it's underperformed when the two modalities are not the same equivalence, have not the same importance.
I see, all right, thank you so much.
Any other questions? Okay, I have a question. And now you classify the patient into 3 groups, and you include a lot of clinical data using the tabular data and also the echocardiogram yet, right? So can you separate the relative importance of table data and also the imaging data? Because the mainly information, clinical information, may be hidden in the clinical table data.
Yeah. Actually, yes, if I understand your question well, the main information is in the clinical data because the tabular data, as they have been made, include echographic generally. So it is rather generally sufficient to perform satisfying classification, but when we want to reach some thresholds of very, very good performance, we need another modality that is more fine-grained. That's why the multimodal scheme is helpful.
So, any question from the crowd? Okay, then thank you very much.
Thank you.
Okay, the next paper is imitating radiological scoring, a global local attention model for 3D chest CT volumes, multi-label and anomaly classification, presented by Theo. Yeah. Theo Di Piazza.
Thank you. Okay. Hello everyone. Thank you for being present for this session. My name is Theo and I will present you our work regarding the introduction of a new model for multi-label anomaly classification from 3D CT volume. To give you some context and motivation, as you may know, computed tomography is a very important modality because it allows radiologists to have a very detailed view of the patient body in order to detect anomalies. However, there are more and more scans to analyze, so there is a need to develop automated tools to support radiologists managing this increasing workload. Among these tasks, much effort have been done regarding segmentation, anomaly detection, and more recently, report generation. However, the multi-label anomaly classification task remains challenging due to the high variety of anomalies to observe. For example, in the figure, there is a need to develop robust method that can classify small anomalies, such as calcification on your left in orange, but also bigger and more diffuse anomalies, such as cardiomegaly in green on your right. In this work, we will only focus on 3D chest CT scan, so we will leverage the CT-rate public dataset, which consists of more than 20,000 unique patients from a Turkish hospital, and for each volume we have 18 labels, which are extracted from radiology reports. And on your right, as you can see, we will perform a cross-dataset evaluation from a public dataset from United States called ROD Chest CT, which consists of 1,300 unique patients with 18 anomalies shared with the CT-rate dataset. Regarding related work, first approaches were based on fully convolutional neural network, where they simply give the 3D volume through CNN to predict anomalies. More recently, as you can see on the right, CTNet was introduced. It's a 2.5D method because they group axial slices 3 by 3, and they give each triplet of axial slices to a 2D ResNet to extract a feature map. Then those feature maps are concatenated and given to a small CNN for dimensionality reduction, and then a classification head for prediction. An alternative to CNN, which may be limited by their ability to model long-range dependency, are transformers. On your left, as you can see, VVIT, which stands for Video Vision Transformers, were extended from vision transformer, where they work with 3D mini patches, which interact with the attention mechanism thanks to spatial and temporal attention. And on your right, Swin 3D, which is extended from Swin, where they allow mini patches to interact within windows, small windows. However, transformers neural network might be difficult to train, and they often require a large-scale dataset and a large-scale pre-training on same domain dataset to have very good performances. And this method do not explicitly model the way radiologist analyzes a CT scan. That's why in our work, we try to propose an architecture who try to emulate the scrolling behavior of radiologist. So when a radiologist analyzes a 3D CT scan, first, he often navigates across axial slices for global understanding in order to understand the main anatomical region and to have his first suspicions of anomaly to detect. Then, once this is done, he often comes back to axial slices where he has a suspicion of anomalies, and he scrolls back and forth across adjacent slices to confirm his diagnosis by incorporating local contextual information. That's why our work takes inspiration from CTNet, because we try to model the 3D volume as a sequence of a triplet of axial slices. Each triplet of axial slices is embedded in a compact vector representation in yellow, as you can see in the figure. So here we will have 80 triplet axial slices, so 80 visual features, thanks to a 2D ResNet followed by a global average pooling, which maps each feature maps to a compact vector representation. Then those visual features are given to what we introduced as the scrolling block, which is a block consisting of 3 transformer encoders. The first one introduced global attention in order to emulate the first scroll of radiologist across axial slices. So it's a classic transformer encoder where each visual token can interact with all others. Then we introduce local attention with what we call caudal cranial sliding window attention. Here is a simplification of the intention mask we use in this module. We try to emulate a scroll from the radiologist from the caudal to the cranial direction, such as each visual feature, which correspond to a triplet of axial slices, can only interact with Q axial triplet slices below itself. Then, to emulate the back and forth scroll, we have to do the opposite. So we do the cranial to caudal scroll, which is similar. It's a sliding windows attention, but in the other direction, where each triplet of axial slices can interact with Q, a triplet of axial slices above itself. And Q is a parameter that can be tuned, and I will show it later. Then it results in 80 updated features, which are aggregated with mean pooling and given to a classification head. Regarding quantitative result, we compare against various backbones, such as VIVIT, SWIN, and CTNet, with traditional metrics, AROC, accuracy, and F1 score. As you can see on the first dataset, CT scroll yields the best results. And when we perform a PERT test between our metrics and the one of baseline, we obtain a p-value below 0.01, suggesting a statistical significance of improvement. And finally, observations are the same on the cross-dataset evaluation, since our proposed model CT scroll yields the best result. So as our work focuses on feature reduction and feature interaction, we perform an ablation study first on feature reduction, where we compare 3 modules, 3D convolutional network, which is the one from CTNet, a simple linear projection from flattened feature maps and a simple global average pooling, followed by a classification head. As you can see, a global average pooling slightly improved the F1 score. And then we also compare different interaction modules, specifically different attention masks in transformer encoders. And as you can see, the scrolling block highlighted in orange yields the best results compared to causal, self-attention, or an alternating between global and local attention. Finally, we also performed a quick ablation study on the window size Q, which restricts the field of view during the local attention. As you can see, 16 yields the best result, so we used 16 in all of our experiments. Finally, an advantage of using a 2.5D approach is that as we use a 2D ResNet to obtain a visual feature, we can extract heat map with GradCam. And as you can see, for various anomalies, the model effectively seems to classify from relevant regions for diffuse anomalies such as cardiomegaly or smaller ones, such as, for example, pleural effusion in the middle. Finally, about future work, a first proposition, as we work with a 2.5D method, we can take full advantage of the third dimension by introducing a 3D CNN module for local feature enhancement. Another idea will be to introduce more supervision with a segmentation step in order, for example, to help the model to focus on relevant regions depending on anatomical segmentation. And as a conclusion, our main contribution is the introduction of the scrolling block, which consists of an alternating between global and local attention, which seems to help the model to focus on relevant regions and to model both short and long range dependency effectively to detect anomalies. And finally, I give you at the bottom the three main references and the data set that we use. Thank you for listening.
Thank you very much for this nice talk. Ron, please go ahead.
Okay, so I'm a radiologist and I do scroll when I interpret scans. I'm trying to understand why this works, because one of the reasons I have to scroll is that it's hard to appreciate the three-dimensionality of an organ. And so I scroll in order to see the full three-dimensionality when I'm looking for lung nodules or liver lesions or whatever. So I can sort of understand what you're trying to accomplish here, but if you have a network that is inherently 3D to begin with, how does the scrolling benefit?
So you mean how I can introduce the scrolling in the 3D networks? I'm
Well,
not sure if I understood the question.
Well, my feeling is that one of the reasons as a human looking at an image, one scrolls in order to get the 3D information. So if one uses an AI algorithm that's inherently 3D to begin with, why do you need to scroll? Why do you need to emulate scrolling?
Here, if we used a fully 3D networks, I think we will not need to emulate scrolling, if it was the question.
Yeah.
Here, it's maybe a special case where we only work with a 2.5D network, meaning that each feature is an image, like a triplet of axial slices, and maybe an alternative to aggregate features is by trying to emulate the way radiologists work, meaning that when they see an axial slices, they scroll in order to incorporate local information from adjacent slices, maybe to confirm their diagnosis. I'm not sure if I answered the question correctly.
Maybe we'll take it offline.
Okay.
Okay, we have time for another question. So I'm sorry if I might have missed it, but you have two data sets, CT rate and blood tests. Have you tried zero-shot experiments? Does something trained on one data set translate to the other, or vice versa? Would you be able to hypothesize if it would generalize?
We only train on the CT rate dataset and evaluate, perform like inference on the other one. But it will be interesting.
And not the other way around.
Yeah.
Yeah, sure. Okay, then let's thank the speaker again.
Okay, I'd like to invite the next speaker to present improving brain disorder diagnosis with advanced brain function representation and common law unknown network. And welcome, Tyler.
All right, thank you for the introduction, and thank you for saying the very long title of my paper, so I don't have to. My name is Tyler. I'm a PhD student from the University of Kentucky, and I'm going to be presenting my work today, done in collaboration with my advisor, Dr. Imran. So, as you can tell from the title, the focus of this paper will be on improving brain disorder diagnosis. Specifically, the brain disorder that we're looking to improve the diagnosis of, in terms of classification, is autism spectrum disorder, or ASD. You can see on the screen now some statistics and some symptoms of ASD. As you can tell by the chart on the left, that in the 21st century, the number of children diagnosed with autism spectrum disorder is growing and continues to grow as our understanding of the full spectrum of the disorder continues to grow. And with that growth in understanding comes to the need to improve our methods of diagnosis, particularly in terms of AI-based methods for diagnosis. So traditionally, the diagnosis of ASD using AI-based methods has come from the quantification of functional connectivity, or FC, from resting state fMRI scans. And traditionally, FC has been computed via ROI parcellization from brain atlases, which you can see an example of on the screen. So basically where you map each patient's MRI scan to this atlas for consistency. However, the use of atlases such as these does come with some inherent flaws. We've highlighted some of them here. So the first is subjective selection bias. So if a researcher knows that the selection of a certain atlas will improve their results, it may look good for their paper, but that may cause some issues in terms of reproducibility if other people try to replicate it and they use a different atlas, and we want to avoid that. So we need some kind of atlas agnostic methods. The second is that mapping each individual patient to a template like an atlas can harm the individual specificity of each patient. You can lose some patient-specific information that could be beneficial for diagnosis. And then the third is, in a similar vein, use of an atlas you could lose some of the interaction between different brain regions in terms of the connectivity. So all of these flaws basically highlight the need to move to more methods using AI that don't rely on the mapping of ROI parcellization using atlases such as these. So that takes us to the contributions that I'll be discussing today that we propose. So I'm going to be proposing a model called ABFR-CAN. It is a transformer-based network for ASD classification from resting state fMRIs. And as you can see, it makes use of the Kolmogorov-Arnold network, or CANS, which is a fairly recent architecture released last year. And I'll get more into that in a second. And I'm also going to talk about some proposed methods of improving the actual functional representation of the brain prior to feeding it into our proposed transformer network. And then I'll be talking about a lot of experiments with different configurations of CANs within two different transformer backbones. But first thing first, the difference between CANs. So CANs were initially proposed as a potential alternative to the multi-layer perceptron. You can see kind of visualizations of both of them on the screen here. So multi-layer perceptrons have fixed activation functions on nodes and learnable weights on edges, while CANs have learnable activation functions on the edges and some operations on the nodes. And the general idea of CANs was that they could perhaps better and more efficiently model complex functions such as the functional connectivity that's present in our brain. So this is a diagram showing our ABFR-CAN architecture. So the first part of it, this is the actual transformer-based method. It should look fairly familiar. It's just modified to process brain functional representation information. I'll talk about how it does that momentarily. But mainly the contribution here that I'm going to be discussing in terms of CANs is there are two main areas within a transformer that you could swap out MLP components with a CAN. The first is in the encoder, and then the second is in the classification head that'll make the prediction. So in our experiments, when I talk about replacing MLPs with CANs, this is what that's going to look like. So basically the replacement is swapping out an MLP block in the different parts of the transformer with this CAN block here. The core of this CAN block is the CAN layer. And this is a visualization here. And then, so I'll come back to this transformer architecture as I get near discussing the results. But first, I want to talk about kind of what happens before we get to the actual transformer-based classification. And to do that, we need to understand a baseline method that we'll be using to compare our proposed approach to. This is called random FR. This is basically a method that was proposed last year in IEEE TMI, meant to move away from the use of atlases for functional connectivity representation. It involves 3 stages. The first is sampling, and here, instead of relying on RI parcellization from an atlas, the way it works is each patient's MRI scan is anchor patches are sampled directly from the scan for each patient, and then blood oxygen level dependent signals or bold signals are then extracted from each of the anchor regions as well as the positional coordinates for each region. That then goes to the second stage of the architecture, the functional representation. So you have the anchor regions defined. Next, you have to represent the actual brain function for each patient. The way that is done is by then sampling a number of patches from each of the anchor regions, calculating their bold signals, and then computing, it's called functional connectivity matrices, or FC matrices, for each of the patients, which is basically the Pearson correlation between the bold signals of the sampled patches compared to the anchor patches. And then the position descriptions, so basically the position coordinates from those sampled patches. And then they're fed into a transformer network where they're combined, and through multi-head self-prediction, the transformer learns that functional and positional information and produces a class prediction. So in terms of our contributions compared to this baseline, we make 3 main changes. The first, obviously I discussed earlier, was the use of CANs in place of MLPs. The second comes in how we select the anchor regions from the fMRI scans. So each of the scans, we select the anchor patches from the gray matter region of the brain, which is traditionally used for FC quantification. The middle, this grid-based anchor selection method, is the way our baseline method utilized it. So as you can see, the anchor regions were selected in a grid where it basically just in a sequential manner go in a grid pattern until you've sampled the appropriate number of anchor regions. We suggest doing it in a randomized manner as opposed to this grid-based method, mainly to kind of increase the diversity of the representations and also hopefully capture better the subject level representation of the brain. In terms of the actual patch sampling process from the anchor regions, this is the baseline, so just kind of randomly sampled using one scale. We propose moving to an iterative patch sampling process where you sample the patches once and then go back, increase the scale of the patch, sample again, and do it a 3rd time. And basically this serves as kind of a 2-thing, creating a multi-scale representation for each patient's function. And basically that also serves as a form of data augmentation to increase the amount of patches. So once we've done both of these things, we then pass to our transformer, and I'll talk now about the experimental setup that we used. So the data set we used for ASD classification came from the Autism Brain Imaging Data Exchange, or ABIDE, and we used data from 2 different sites of ABIDE. You can see them here. We use the NYU site and the UM site. And in these figures, you can see the statistics of the patients in terms of ASD versus control that we had. We evaluate our ABFR CAN approach using 2 different transformer networks. The first is a traditional vision transformer that you see on the left, and that was discussed earlier. The second is a data efficient image transformer, or DEET, which you see here. And as with the VIT that I discussed earlier. In the deed, there are 2 locations that we replace MLP blocks with cans. They are, again, in the encoder and the classification head. So moving to the first of our experiments, this is a direct baseline comparison with just the grid-based anchor selection and the random patch sampling method used in the baseline, just swapping out with can components. We evaluate on 6 different classification metrics: accuracy, AUC, F1, precision, sensitivity, and specificity. Each of the transformer backbones is compared with 4 different configurations. So MLP, MLP, so all MLPs, can, so swapping out cans for both MLP components, and then a hybrid. So MLP can is swapping out the classification head only, and then can MLP is swapping out the encoder only. So here you can see the results for the VIT and DIT configurations. So MLP can perform the best for VIT, and then can perform the best for DIT under the baseline setting. Moving to our proposed random anchor selection and random patch sampling, which is the baseline, in the same experimental setup, you can see that can swaps to perform the best for VIT, and then MLP can performs the best for DIT. Going back to the traditional grid-based anchor selection, and then with our proposed iterative patch sampling process, you see that can MLP performs the best for VIT, and then can MLP performs the best for DIT. So both of them were the same this time. You'll notice that there's some variance going on so far between the best performing configurations for each experiment. And then this experiment is basically all of our proposed contributions together. So random anchor selection, iterative patch sampling, and then with the can configurations. So here MLP can performs the best for VIT, and then MLP performs best for DIT. So all of these results so far were shown on the NYU site. To show on a different site, we show the results for UM. Here can perform the best for both. To investigate the cross-site generalizability of our proposed method, we trained on NYU and tested on UM, and then did the opposite, so train on UM, test on NYU. You can see those results reported here. So all of these metrics can perform the best. So we then compared using all of our proposed approaches with state-of-the-art baselines, and you see our ABFR can approach performed the best against 7 different state-of-the-art ASD classification methods. So in conclusion, we propose a transformer-based method for ASD classification, as well as some methods of improving brain functional representation for each patient. We found that random anchor selection and iterative patch sampling performed the best. And then we found that overall our can configurations are replacing all MLPs with cans perform the best as well. I now yield to any questions, and you can also find links to our paper and code at the poster session after this, and I'm more than happy to take questions there as well. Thank you.
Thank you for the nice talk. And any question from the audience? Okay. I have a question for you, and because functional MRI is a really complicated procedure, so you have 2 data sets. So do they have the same protocol so that they can be used to be compared?
So they use 2 different sites. The scanning parameters did differ between the sites. So basically in our experiments, we did kind of investigate what happens when you train on one, test on the other. There is a slight performance drop when doing that, as would be expected between the difference in parameters. However, if you did have a data set that was all taken from one site or multi-site data that was all processed the same way, you would expect that you would have the same performance between them.
Hi. I thought that this random anchor selection was interesting, but I noticed in your picture it didn't seem to cover the entire image after all of in your little example image. I was wondering if that was something you were concerned about, was just missing some of the areas, like there's this part in the lower left that's just not hitting as much.
Yeah.
Or if you're trying to balance it out. For
sure. So in doing these experiments, you can set the number of anchor patches that you want. 100 were used here for that. In order for this to work, all regions within the gray matter don't have to be selected because different regions within the gray matter are more reflected of showing differences between patients that are control and ASD. But if you wanted to capture the whole gray matter region, you could simply increase the number of anchor patch sessions, but it shouldn't decrease performance that much to not capturing the whole region.
Did you notice any difference of like increasing, decreasing this number?
If you decreased it, we tend to just see like performance degradation. Increasing it didn't help much, so this is a solid.
Yeah. Thank you.
Yeah.
Due to the time constraint, thank you very much for your nice talk, and we move to the next topic. Thank you.
Okay, the last paper of this session is machine learning with scarce data, ejection fraction prediction using Plex view. The paper is presented by Chi-Yuan Guo.
Yeah.
Yeah.
How do I set it to the present mode? Cool. All right. Hi everyone, I'm Jeffrey and I come from Caltech. Today I will talk about our work about ejection fraction estimation from PLAX view, so the parasternal lung axis view. Here's my talk outline. So first I will share a little bit about the background and our motivation. And second, I will talk a little about the prior studies and the bottleneck of the prior studies. And third, and most importantly, I will talk about how we curated and created the data set and how we trained the model. And last, I will share what our future plans are. All right, first, the background. So why EF, why ejection fraction, and why PLAX view? To give a little bit more background, heart failure really is the #1 cause of death globally, and it costs US alone more than $6 billion annually, so that really is a huge burden. And the ejection fraction, or EF, it is the key for diagnosing heart failure. It measures the percentage of blood left ventricle pumps out, so basically it measures how strong your heart is. And yeah. And clinically, EF is typically assessed with apical echo views in ultrasound. So the top image is an apical 4-chamber view, which is a mainstream method for current AI tools to evaluate ejection fraction. However, we propose using a different view, the PLAX view, the bottom image, which is the parasternal lung axis view. It is not routinely used for EF prediction. So why do we want to use PLAX? First and most importantly, it is just easier and more stable to acquire. So as you can see in the top image, that is the A4C view acquisition process. So it's from the lower chest area, a little bit near the belly area. So it's from bottom up toward your heart. And for PLAX, it's from your upper chest down toward your heart. And especially for those who are obese or elderly, they tend to have fat accumulated in their lower part of body. This can become issues to get a clear enough ultrasound view, especially for the current popular point of care or handheld devices. They are not powerful enough. And secondly, the PLAX view is very common in routine echo exams. And yeah, of course, with a new view, we can improve accuracy from a new perspective. And then I'll talk a little bit about the prior studies. Yeah, so prior studies were limited. The GOCO team, they achieved a MAE, or mean absolute error, for around 8.5%, which was not accurate enough. And XOAI, that's a private company, they achieved a decent MAE for around 7.3, but they didn't disclose any details, so no model, no no algorithm, no data set, nothing is disclosed. So that is not helpful. And as for our model, we achieved 6.86% of MAE, and it really is the first reproducible benchmark, and it matches the capability of expert cardiologists. The reason for the failure of prior studies really is the data scarcity. So there is just simply no public PLAX data set with like high quality EF labels. So yeah, in order to solve this bottleneck, we decided to create our own data set using public data sets. All right, before talking into how we curated our data sets, there are two important models that we trained. The first one is a A4C model. So we utilized the EchoNet dynamic dataset. It's a dataset curated by a Stanford team. There are around 10,000 A4C view videos, and those are with ejection fraction labels. So it's a great dataset, and it's pretty straightforward to train the model that can predict ejection fraction from A4C views from this dataset. So that's our first model, the A4C model. And the second one is called video view classifier, which is also crucial for the later dataset curation. So we first reused the first dataset, the A4C dataset with 10,000 A4C videos, and then we utilized a second dataset called EchoNet LV Edge. It's a dataset from another Stanford team. It contains 12,000 PLAX videos in it. But unfortunately, it is without EF labels. So we cannot just take that dataset and train a PLAX model, which was our goal. And that is our second part of the data. The third part comes from a dataset called Mimic4 Echo. It's a quite popular and very huge dataset. But the thing about it is that it is really messy. So there are so many, there are around 100,000 videos, ultrasound videos in it, but they are not labeled, and it's just very messy. And we extracted around 14,000 other video types videos from them. So other video types except for A4C and PLAX. Yeah, I will not cover the detail how we extracted the other videos now, but all the details are covered in our paper. So you are more than welcome to check our paper out. And yeah, with those three different parts of data, we are able to train our video view classifier. Yeah, with those two models, we are able to build our training data set. So we utilized the Mimic4 Echo data set again, and we applied the previously trained video view classifier to it. And as a result, we get around 5,000 studies, and those studies are with at least one A4C view video and one PLAX view video. So yeah, and we take the A4C videos from those studies and applied the previously trained A4C model to those videos, and we get EF labels for those A4C videos. And we know that for the same study, both the A4C video and the PLAX video must have the same label, must have the same EF value. So we can apply the A4C generated ejection fraction value to the PLAX videos. And that's how we curated this around 25,000 PLAX videos with ejection fraction proxy labels. And those proxy labels are from the A4C model. But as you can tell, inherently, this will have a compound error from the A4C model, since the labels are generated from it. So we created another data set called testing data set. We utilized another data set called Mimic4 Note data set, together with the previous Mimic4 Echo data set. The thing about those two data sets is that they don't correlate to each other. so they don't really have a relation. They don't really map with each other. And what we did is that we take the timestamps of both the data set, and for the same study, if the echo video and the note are taken within 1 day, we consider those video and note are a pair. And with that method, we extracted around 300 studies and 700 PLAX videos from the data sets. And those nodes are very messy, by the way. The meaningful node data set is very messy. It's just in a very messy text format. Therefore, we utilize the GPT-4 API to extract ejection fraction labels from those messy nodes. And that's how we created the testing data set. All right, to sum up, we utilized the training data set and trained the model. And in the testing data set, we got a testing MAE of 6.86%, which matches the FOC tools as well as the expert cardiologist. And it is the first reproducible PLAX benchmark. Everything, the model, the data set is published online in GitHub. And the important technique we use is called proxy labeling from FOC views. And yeah, here's another technique we use. So it's called from image to video classifier. That's how we generated the previous 14,000 other video types. But due to time limit, I will not share that in detail in the presentation. All right, lastly, I will talk about our future work plans. So we are working on, of course, integrating a multi-well EF fusion approach, that is integrating PLAX and FOC view together to get a much more accurate performance. And we are actively collaborating with one of the biggest heart hospitals in the US to ensure domain generalization to external hospitals. And we are also trying to bring our research results into real-world clinics. That is, we are building a real-time feedback iOS application that allows a newbie to navigate and get an automated diagnosis using only an iPhone and a handheld device. Yeah, that's my talk. Thank you very much for listening, and you are welcome to my poster today.
Thank you very much. Okay, we have time for 2 questions. Any questions? And probably I'll start with one. So I was curious if you also performed some sort of subgroup analysis, say across various ejection fraction level, degrees of ejection fraction, quality, PLAX video quality, disease groups or anything. Have you done any subgroup analysis here?
Can you repeat the question?
The question is if you also analyzed a little bit more fine-grained subgroups, for example, the lower ranges of EF, the higher ranges of EF, the middle ranges of EF, how they're distributed and how kind of model performances are also working there.
Oh, yeah, right. So for this data set, the lower part of EF data is more limited. So towards the lower end, the performance really degraded a little bit. But yeah, I have included everything in the paper. So yeah.
And do you also have quality assessment? Some of the videos might have good kind of ejection fraction range, but are probably lower quality. Do you have any surrogates for video quality as well?
Yes, for that I have fine-tuned the video view classifier, and I would say the data point, the videos in the data set is towards the high quality end. Yeah.
Very good. Any further questions? If this is not the case, then let's thank the speaker again. Let's thank all the speakers of this session again. And this concludes the session, and you're released for coffee break. Thank you very much. Thank you. quite a bit too fast.
I can kind of see the screen.
I went there and shouted that they started. So, again, I have news about food, so that's my purpose for being here. That worked, yeah. So, so tonight's dinner is going to be at the Natural History Museum of Utah, and it starts at 6:30, but shuttles will be starting to leave from here at 6 p.m., just from those doors there next to the registration. Okay. So, yeah, that's my announcement.
Okay, thank you. Okay, hello everyone. As a reminder, I'm Tal Arbel. I was one of the co-founders and the editor-in-chief of the Melba Journal, so I'd like to welcome you to the Melba MIDL oral session. So just to tell you a little bit about Melba, Melba is the Machine Learning for Biomedical Imaging Journal, and it's a web-based journal devoted to free and unrestricted access of high-quality articles, really at the intersection of machine learning and biomedical imaging. We launched Melba at MIDL 2020 as a special issue of MIDL. We launched an official strategic partnership in 2022 when these two models were established. The first is the MIDL to Melba special issue or conference to journal track, where a selected number of conference papers are invited to bring their extended version of their papers into journal-length submissions at Melba. And the second is the Melba Middle Journal to Conference model, where Melba papers that were published all throughout the year are now automatically invited to present their work as orals and posters at the Middle Conference that year. So today we're going to have two orals, and the session chairs are Ipek Oges, who's one of the executive editors at Melba, and OL, whose last name? Kavadek, who is our very important publishing editor and just has a lot of roles at Melba, so thank you. So they will introduce the speakers, and I will hand it over to them. Right? Thank you. Yeah. Oops, sorry, there are many things up. So I'll let you.
All right. So the first speaker is.
How do you actually say your name? How do you actually say your name?
Oh, it's Gervadek. Not Gervadek.
Thank you. Okay, thank you.
But yeah, to the science. So the first talk this afternoon is understanding differences in applying DATR to natural and medical imaging from Yonghi Chu. So you can come on stage. And as this is presentation from journal papers, this will be a bit longer than the regular orals we had through the day. So you have between 15 and 20 minutes to present. And it should be in a special folder on the computer.
Yep, it's not showing the. Do you want the presenter read? Yeah. Can we see the presenter view?
Yeah, so.
Some things never improve over the years, so it's printing and displaying slides. But we'll get to it.
Anyone know how to use a computer? But does the animation work if this is the view?
This should work.
Okay, that's fine.
Just
if you cannot make it.
no, it was working. So
Yeah.
we tested it before.
Okay, great. Okay. Hello. Thank you, Melba, for organizing this session. And my name is Yan Qixu. I'm from New York University. Today, I'm going to talk about our recent work on understanding the differences in applying DETR, a popular transformer-based object detector, to natural images versus medical images. Okay, so let's start by taking a closer look at the differences, the morphological differences between medical versus natural images. First, in terms of the overall appearance, you can see that the medical images are usually in grayscale and they're much higher in resolution. So here I'm showing a true size ratio comparison between a mammogram and a natural image from the MS COCO dataset. So you can clearly see that how much larger the medical images are. Secondly, the background of medical images are much simpler. So in natural images, they vary widely from city views to wild views or indoor crowded spaces, whereas medical images are usually acquired through standardized protocols, and they're mostly focusing on a single body part, so that the background is usually just purely black or homogeneous tissues. So the background structure of medical images are much more uniform. Thirdly, the foreground of the medical images are much sparser. And by sparse, I mean they have fewer objects of interest on per image. Sorry. Here I'm showing you that on the MS COCO dataset, you can have ranging from 1 to 50 objects on a single image. However, on the medical datasets, you mostly have only one object per image, and you can really have more than 5 objects. And there are fewer objects, but there are also smaller region of interest. So the objects are much smaller. So most of the objects taken only up to 1% of the entire image, where on the natural image dataset you can have like up to 70% of the entire image. So the idea is that those differences are not just visual, and they can produce consequences on the performance of the detection models. So the DTR, the detection transformer, has been a state-of-the-art transformer-based object detector recently. They are favored because they have this end-to-end training pipeline, so that they remove those handcrafted post-processing steps like non-maximum suppression. They also remove the anchors, and they also utilize transformer to capture long-term dependencies and global contexts. So here I'm showing architecture of a deformable DETR, which is one of the most popular DETR architecture. And you can see that it consists of a backbone and an encoder-decoder architecture. The backbone extracts the features from the images, and they combine a feature from different feature levels, and they're feed into the encoder-decoder layer. And the attention that used in the encoder-decoder architecture is called deformable attention, and that's why it's called deformable DETR. So it's a special type of self-attention that only perform attention on a selective set of important tokens to improve the efficiency. One of the biggest contribution of DETR is its object queries. So the object queries are randomly initialized. They're injected into the decoder, and through each layer, it learns from the encoded features through cross-attention. And once they are output from the decoder, each one of it is matched to either an object or a background. So overall, they can be learned with a set prediction loss. So the deformable DETR provides you with a lean and elegant architecture for detection tasks. So over the past few years, there has been a number of DETR-based models that have been developed with the goal of improving detection performance and also improving the training efficiency using MS COCO dataset as the benchmark dataset. So here I'm showing you the number of architectural modifications has been added to the original DETR architecture over time. So you can see that as we have those progressively more and more complicated architectures, the performance gain is limited. It's incremental, I would say. So that leads us to the question we're asking is that, are those overcomplicated architectures really suitable for medical images? So our hypothesis is that a simpler model might work just as well or even better than those highly engineered DETR variants. So to test our hypothesis, we systematically conduct experiments on 6 different design choices. They're simple design choices, and we found that first, if you slightly reduce the input resolution, and if you remove the encoder layers, and also you remove the multi-scale feature fusion, also reduce the number of object queries, removing those 2 decoding techniques that has been introduced by to deformable DETR, you get much higher training efficiency without sacrificing any performance. So for the rest of the talk, I will just be focusing on those 3 design choices. Yeah. Okay. So we conducted experiments on 2 representative data sets. One is a breast cancer screening data set. The task is to perform malignant lesion detection. And the other is a Luna-16 long nodule detection data set. Those 2 data sets represent those characteristics we just described earlier. They're high resolution, they have simple background, they have small region of interest, and they only have a few objects per image. And to increase the generalizability of our result, we also tested out on 2 backbones. One is a convolutional-based backbone, ResNet, and another is a transformer-based backbone, swing transformer. Okay, so the first finding is that the encoder is redundant if the backbone is powerful enough. So here I'm showing you that the detection performance as we vary the number of encoder layers from 0 to 6. So it's surprisingly to see that when we completely remove the encoder layer, it doesn't really hurt the performance that much. And another note is that if you're using a convolutional-based backbone, then you probably need at least one. You probably need one encoder layer to transform the future space from convolution to attention, like transformer. So this also applied to the Luna-16 dataset. Although you can see that when we completely remove the encoder, the model just doesn't really work. Okay, and that's because we did not pre-train on the backbone for this Luna dataset, but we pre-trained before. This is another takeaway, is that if the model is not domain adapted, then you probably need at least one encoder layer. So the overall idea is that if you have a powerful and domain adapted backbone, then you don't really need the encoder. The encoder is redundant. And you can increase the training efficiency by 40% without losing the performance. Our second finding is about the multi-scale feature fusion. So we find that the benefit of multi-scale feature fusion is less pronounced for medical images. So here it's just one of the example of the multi-scale feature fusion, just to give you an idea of what is that. So you have the idea is very simple. You have a convolutional, or you have any kind of backbone, and then you take the feature maps from different levels, from low-level details to high-level semantic information, and then you combine those feature maps using any kind of method you want, normally just concatenation, and you use the combined feature for the detection task. Okay, for this one, our result shows you that using a single level feature map achieve comparable performance, and somewhat even slightly better performance than using full-scale feature fusion. And for the mammogram dataset, using the high-level feature is enough. But for Luna-16, you need an intermediate level because the objects on the Luna-16 dataset is too small and cannot be seen on those the highest level feature map. So why is it the case? So the multi-scale feature fusion is useful particularly on non-iconic natural images. That means they have overlapping, cluttered objects, and also the objects in different scales. And the multi-scale feature fusion helps by attending to different feature levels to predict objects of different scales. But it's not the case in medical images. As we have shown before, we rarely have overlapping objects, and the object sizes also, they don't vary much. they have like very uniform small sizes. So here, the multi-scale feature fusion doesn't offer much benefit here. Okay. Our third finding is about the number of object queries. So the number of object queries determines how many objects you can predict on a single image. So it's natural to think as we increase the number of object queries, you can increase the possibility of predicting an object, and then you can improve the performance. But our experiment shows that's not the case. The performance is saturated once you have reached 100 object queries on medical data set. And okay, why is that the case? We evaluate the model's localization performance versus classification performance separately. So when we are looking at the localization performance, that is basically the percentage of the objects that being correctly localized, meaning they're putting a bounding box with. So you can see those dashed line on both data sets, they keep increasing as we increasing the object queries. However, if you look at the solid line, the classification performance drops. And that means that you are creating a lot of false positives by adding more and more object queries. So here we claim that on medical images, it's easy to localize the abnormalities, but it's difficult to differentiate the false positives from the true positives. But however, in natural images, localization is much more difficult because you have all overlapping objects, and they have objects of different scales, so it's harder to find the boundaries of all the objects. And this suggests that all the techniques that aim at improving localization, which is most of the technique that has been developed based on natural image object detector, they don't really, they might be just unnecessary in medical imaging. And not only the object queries, we also tested out the other two decoding technique that aim for localization. They also didn't really help, and we think this is the reason. Okay, here I'm showing some visualizations of how our AI model failed on the medical imaging object detection. So here, you can see that the model localized well. So the predicted bounding boxes overlapped with the ground truth one. However, the model give them a really low classification score, although all of them are malignant lesions. So we talked to a radiologist, and those malignant lesions are not simple malignant lesions. They are difficult cases. They resemble certain characteristics from those benign findings or normal anatomies, means that they're basically low density and they're circumscribed masses. So again, here, what we are thinking is that the goal is to build a better classification model that can tell the false positive from the true positive. Okay, so in summary, we believe that a simpler architecture can give better performance for medical images, and we present this simple recipe for designing our DETR for medical data. This could be a very good start point if you want to improving the classification head of this architecture. Okay, thanks all my collaborators, and thank you so much for listening.
Okay, thank you for your nice presentation. We have now some time for questions, if we have any in the audience. There are 2 microphones where you can go. But in the meantime, I have first a high-level question is basically, well, asking your opinion on how much you think we should follow what's happening in the big AI conference, if basically for medical application we need to take what they have and remove stuff and then get better performance, but
can you like, it's a open.
how much do you think, should we still attend CPR? That's very...
I mean, I'm much more surprised than maybe you guys when we find out that removing those stuff doesn't really hurt the performance. And I think this tells you the idea of how we should do medical imaging architectural design, that is to simplify things before you add more things. And you don't need to take a CVPR architecture that's designed for natural images and then just directly put it into our medical data. And then you think, oh, something doesn't work, we need to add another module. And then you have an overly complicated architecture, and it's not. I feel like we should do the other way, to look at each module, what each one actually works, and take something that's not necessary first before we add more stuff. Yeah.
Yeah. Well, that's why we are here at MIDL. That's good. Well, Tolga has a question.
Yeah. Thank you for the presentation. Very nice work. I was just wondering about the multi-scale future fusion part of your work. In this part, did you experiment with also pathology images? I wonder if there would be a difference there, because there's scale differences in the structures that we see maybe compared to radiology. What's your opinion on this?
Yeah, we didn't try pathology images because, as I say, medical image as a general term, I also put a lot of restrictions. Like I said, they're single scale, grayscale, and they're, so that doesn't really, I was thinking about that earlier. I feel like pathology can be slightly different because there are a lot of things happening in one single pathology image, rather than for radiology images, there's only like one abnormality or maybe at least two, you know. So I don't know, I can't answer that, but it's a very good question. Thank you.
Thank you. It was a good presentation. I have a question. I think I missed when you discussed about number of encoders impact when you have transformer base versus backbone versus CNN backbone. Can you go back to that slide?
Yes. Oh yes, this one. Right.
So here, do you see like you need more encoder layers for the transformer backbone compared to CNN backbone? Is that what you're trying to say here?
This is just, yeah, that's a good catch. I was just talking about how you remove the encoder completely from 0 to 1. You have slightly more performance improvement than here when you're using a swing, a transformer-based backbone. So that I'm saying that maybe adding at least one encoder layer, it's important for if you are using a convolutional-based backbone. That can give you more benefit. I don't know if that answers your question.
So if you add more layers in CNN base, then you can get better improvement?
If you look at the figure, if you add more, the performance doesn't really improve. But at 1, it's better than 0. I guess that's the idea.
Okay, thank you.
Yeah, thank you for your question.
And last question, I guess.
I have a question that if we have a small region detection task, should we still use methods based on transformers or methods based on simple CNN? Or
can you define what's a small region detection?
Like Luna 16.
I see.
Or even more smaller, like Princeton, some high risk region of head and neck cancer.
I haven't thought about that. But why do you ask this question? It seems like you're assuming that the convolutional is better for detecting small objects, right? Is this?
Well, maybe.
I sort of understand your question because for a transformer you have patch, and that kind of condenses the information into a patch. But here I'm not using like regular transformer, I'm using swing, so that you have different layers. So the information it's contained, like a small object information is contained. That's the reason why we choose a swing instead of the VIT.
Thank you.
Yeah, thanks.
Thanks for the presentation. My question is, do you think the difference you see here is because of the image characteristics between medical image and the natural image, or because we have more images, natural images for training compared to the medical images? Basically, I mean, like if your training size for the medical image is 10 times bigger than this, does your conclusion change or not?
Okay, yeah. The training data set that I'm using for the first tag, it's huge. So we have millions of images. So that I think that would probably solve your question. So it's actually a big data set. But the second task, the Luna 16, is a small data set. So for both data sets, we reached the same conclusion. So I think that solves your question, that it's actually related to the image characteristics rather than the data sizes. Yeah. Thank you.
Well, thank you everyone for the question. Thanks a lot for your nice presentation.
We have our next speaker. Let me come back to this. All right, so we have our next speaker, who's going to be Hao Yu, who's the second author on this paper. He's going to be talking about how to build the best medical image segmentation algorithm using foundation models, a comprehensive empirical study with SAM.
I'm so how do I?
Oh.
It's happening again.
Where is the cursor? Oh, it's over there. We are on the wrong screen, that's why.
It's in the so
If I can-
enable editing.
If I can get my cursor there.
We don't have the best learning rate, but it will come.
And then do presentation. So
Take that.
All right. All right. I want to first thank Melba for holding this, so I can travel here for free. So, also, I want to first acknowledge my advisors, Han-Xue Du, who's also so we are the co-first authors, and Ji-Chen Yang and Majima Zrosti for making this paper possible. Yeah, so for this, we are trying to study about the medical image segmentation, and we are particularly interested in how can we adapt foundation models to this task, given that we all know foundation models might boost the performance when you just apply it. And I also want to mention that it's a really empirical study. So we have really tried just a lot of methods, but we have not really designed something that's like technically novel. Yeah. So to begin with, we have SAM, the sediment anything model, that was proposed, I think, in 2023, and it has shown to be a very strong foundation model for sedimentation. And one of our early work actually studies if we apply SAM directly to the medical domain, what will happen, and we have the results on the right. So you can see, so as you may know, SAM is a prompt-based method, so the type of prompts fed to the network will change the output. But so on the figure here, we have different types of prompts, but even if we look at the maximum median, that's something around 0.7, so I don't think that's that seems to be ineffective if we just want adapt SAM directly. But I mean, that's not saying SAM is not good. It's still an amazing work, given that all the performance are zero shot. So this drives us to think how can we fine tune SAM to the medical domain. Okay. So to begin with, we actually did a literature review. We tried to collect what's the work has been done when we wrote the paper. And we found that we can actually summarize the existing words into several categories that I will provide a definition very soon. So here brings our, I guess, key point about our paper is to basically try to tell you which category should you be using when you want to fine-tune SAM to the medical domain or to your own data sets. So to begin with, we have the category definition here. On the top left panel, we have the overview of SAM's structure. So it has like an image encoder, a mask decoder, and additionally a prompt encoder. But in our study, we actually removed the prompt encoder because we are aiming at automatic segmentation in the end. And I know that there are words that try to generate automatically prompts and feed that to the network. I mean, that is a very legit approach, but just it's beyond the scope of this paper. Okay, so now jumps to our definition of the category. So first, we studied the size of the image encoder. So we just have the different, so the N here, I'll just tell you like the number of layers. So we have 4 layers, which is like the WIT tiny, and that is actually from another paper called Mobile SAM, which just distilled the weights from the original SAM. And we have the WIT-B, the base, and the huge. They are just the official weights from SAM itself. And secondly, we consider about the range of updates. So we found that some words actually only optimize the decoder of SAM. It keeps the encoder untouched, or we can try to try to update everything. And lastly, we study. We find that there are multiple fine-tuning strategies, but mainly it's just between the Valina, which means we just fine-tune all the parameters, and the PEFT, which stands for the parameter efficient fine-tuning methods. And out of the PEFT family, we select the adapter and the LoRa, as well like those two are the popular ones when we wrote the paper. Okay, and the next, we actually also consider about the data availability. So all the stuff I just mentioned we're just assuming that you have a single data being available, a single label data. But what if we have more data? What if we have more labeled data? And what if we have more unlabeled data? So the idea is that we can use those additional data to first fine-tune, I call it continue pre-training SAM. So basically we do something with SAM in addition before we fine-tune it to a data set. So I'll jump to the details later, but one spoiler is that for setup 2, the match SAM can be a really good example there. Okay, and before showing the results, I also want to show our experiment setup. So we have actually collected tons of radiology data, that covers MRI, ultrasound, X-ray, CT, and etc. And we did some pre-processing because SAM itself was 2D. So for the 3D modality like CT and MRI, we just conduct our research on the slice-based. And we try to cover a lot of images, a lot of body parts. And yeah, just realized that we don't have any pathology here. So apologies for the pathology people, but I hope the conclusion we find can be generalized to those data sets. Okay, so next we have the results. So to begin with, we actually, so given the data sets we have, we will fine-tune SAM on each of them, and we will take the average in the end. So each column you see here are the average performance over 17 data sets. And we will compare the selection one by one. So to begin with, we want to compare about the size of the image encoder. So for each group, that's like a 6 columns here. If we took the max, we basically found that the WIT-H, so that's the huge WIT, and the WIT-B, the base WIT, have very similar performance. And both of them outperforms the tiny version, the WIT-tiny, which only has 4 layers of transformers. And next, we compared the range of the, which should we only update the SAM's decoder, or should we update both the encoder and the decoder? So to compare that for each column, you can compare between the red and the blue bar. You can see that there's almost an absolute advantage of adjusting both the encoder and the decoder. So I feel like that gives you some hints, especially to the papers that we found in the literature that only adjust the detotals weights. If for those paper, they see our conclusion, maybe they can have a instant boost in their performance. Yeah, and lastly, we compare about the like which fine-tuning strategy you should be using. So here we have the Valina fine-tuning, which stands for the plus V here. We found it to be working less well for the huge models, for the VIT huge and the VIT base, but it works somewhat good for the VIT T here. I don't know if I can. Okay. I cannot show the cursor here. Yeah, but if you look at the VIT T plus V, so that's like the, you fine-tune all the parameters for the tiny model. You find that to be working actually okay work, but not so good when you have larger image encoders. And we found that using parameter efficient fine-tuning really matters. So once your model becomes larger, that will boost the performance by a considerable amount. But choosing which strategy, I don't think they matter that much, because if you compare between adapter and the LoRa, I think they give similar performance. And just one little, I guess, interesting observation we found that was LoRa. So LoRa was known to be working very well for language-based fine-tuning. And if you consider the case here, you found that the LoRa works really well with the VITH, so like a huge encoder, and its performance drops a bit when you go from VITH to VITB, and then it further drops from the B to T, the tiny version. So, and these kinds suggest that for LoRa, this particular fine-tuning strategy, maybe you really need a huge backbone. Right, so if you think about language models, they have the 7 billion, 14 billion, and even more data sets. That's why potentially LoRa works better. So that's just some interesting findings we also had. I don't think that's like a legit conclusion. All right, so after finding the best performance, we also compare our methods externally with the family of UNet. So on the right figure here, we actually compare the best fine-tuning version SAM versus UNet. And if you look at the last row here, that's the average performance. We get a 2% better performance in terms of dice. So I don't think that is saying you should be using like fine-tuned SAM when you, instead of UNet when you try to segment your own data set. But if you really look at the performance of each individual data set, you can see there is a high variance. For the CT clone data set, we were actually 13% better in terms of dice, and for the prostate, we are 7% better. So I guess that's probably saying fine-tuning SAM can be a strong alternative in addition to UNet. So maybe you can try both methods and see which one works better for your data set. All right, so the results I showed before were just saying, we're just assuming that you have only a single data set that's available during fine-tuning. And now what if we have more data sets? So let's think of a contrary example. Let's say you just want your model to work on a kidney data set, like a CT kidney segmentation. So in addition to your own private data set, you can leverage BTCV, you can leverage the data set from Total Segmentator. Right, so there are just a lot of additional labeled data sets that we assume are available. So how can we leverage those data sets? So the first question is how do we train with those additional data sets? We propose to actually use SAM's own strategy. So intuitively, you can think of this as, so SAM was just trained on its nature images. What if there are some like additional MIDL data that's available during the training? And once we have that version, we just do the fine-tuning, what will happen? And so actually at that time, MADSAM was available. So for those who don't know, so MADSAM is also a strong variation of SAM. in the medical field. It was pre-trained, I think, on millions of radiology data, and it has shown very good performance in terms of segmentation. So we actually use MedSam as the backbone, and let me jump to the. Okay. So this figure shows what happens if we use the. Okay, so let me go one step back. So here we have the gray bar. That's basically the results I just showed you before. So that's the performance of using SAM as the backbone. And then I do fine-tuning on each individual data set, what the performance will be looking like. And the red or the green bars are essentially showing the change when I switch the initial point from SAM's point to MedSam. So I guess the results are not that encouraging because at the very beginning I thought that will actually boost the performance by some %. But in reality, we only see that under one specific setting, the one on the bottom left, the encoder, decoder plus vanilla setting, we see that switching from SAM to MedSam will increase the performance by 5% on average. But on all other settings, you see like an average decrease in the performance. So I don't have a good explanation of why that's happening. So one, probably just because SAM is sort of, MedSam is potentially overfitting to its own trained data set. And for our fine-tuning data set, that was indeed not included in the pre-training data set. So that might be why it hurts the performance. And additionally, we considered about what if there are unlabeled data available. So I feel that's a legit assumption in many cases. So as many hospitals will have a lot of unlabeled data. So essentially, we can do some pre-training with SAM. We can also pre-train with SAM, but in this case, we cannot use supervised loss. So we choose to use MAE as our objective. So MAE is just a very popular self-supervised technique. It will mask some image, and the goal was just to reconstruct the masked region. So one experiment we don't have time to see is, if we have other self-supervised learning techniques that change the performance. That is not yet to be done, but I have originally tried Dino. I found that to be slightly worse than MAE, but I don't have the chance to try, say, Dino V2 or other more recent methods. And another prerequisite for our task is we only pre-train the encoder with MRI data. That is more like my assumption that if you have multimodality data during pre-training, that will, I don't think that will help as much as if you just train on one data. If if your downstream is just MRI, and we just name it as SSL SAM for easier reference. Okay. So now we can show the results. So I want to highlight, if you look at the red bar, which are the highlight regions here, we do see a cool result of that under certain fine-tuning strategy, switching from SAM's encoder to the SSL SAM will boost the performance. So we pre-train. So in this case, our data was pre-trained on MRI, so it does lead to consistent improvements in MRI data sets when compared, but its performance becomes more unpredictable, on other modalities like CT and ultrasound. So let me jump to the conclusion here. So first, if you only have a single data set being available within the WIT-B, so using the base model and update both the encoder and decoder, and use the adapter as your fine-tuning strategy is the recommended one. The performance is slightly worse, like 0.2% worse than using the WIT huge as the backbone. But just realistically, training WIT huge is too expensive, I guess, for most people. And we found that the best strategy actually outperforms UNet by 2%, But again, that is not saying you should try to just fine-tune SAM for all your segmentation, but it may be a good, strong alternative to try if you have additional resources. And yeah, pre-training. And lastly, if you just pre-train the image encoder with MAE, that does help. We pre-train on MRI, so the model becomes better on MRI. I mean, that is kind of expected, but we just prove that. And lastly, we have the code. Just being here, we have everything that you should be able to have everything. And we also have the the weights pre-trained with MAE being available. So if you are interested, you can probably also use that. And yeah, that's it. Thank you.
Thank you for a very nice presentation. We have a burning question that's already lined up.
Yeah. First, thanks so much for the very informative presentation. So my first question is is the test data totally independent from the training in all this experiment?
Yeah, so our setup was, in the setup one, where we only have one single data. We will already split this data set into the training, validation, and the test.
So the testing and the training is actually sometimes comes from the similar data set. Okay.
Yeah.
So the second question is about do you have any insight of the data balance of some training and testing? Because as you show different modalities, MRI, ultrasound. So for example, when you do fine-tuning, you fine-tune on the single modality, right? So and only compare on this single scope.
Yeah.
Okay. Do you have any insight about the influence of batch size and also the mixture of prompt during the training?
Okay. So batch size, I think that affects less. So we really do it based on our availability. So for the WIT-H, we can only feed a batch size of 2. That doesn't mean we don't want to feed more. That's what we can do. We didn't study much on that, but we do use different batch size on different architectures. That doesn't have a much difference. And in terms of the prompts, we do have a preliminary study at the very beginning, where instead of just throwing the prompts away, we will generate pseudo masks from the ground truth, and we will feed that during the training. So in the end, we can feed that with a probability. So in the end, the model can do both automatic segmentation and prompt-based segmentation. What we found was that, at least for our data set, inserting additional prompts doesn't change the performance, versus you just let the model output automatically.
Okay, thank you so much.
Thank you.
Thank you, very nice presentation. I was a little curious about the prompting, actually. How are you doing the prompting? You have so many different applications. And then did you try to also include the prompts in the NN unit, right? You're helping SAM by giving it a prompt. So it's unfair to compare it with the NN unit without that prompt. So I'm just curious if you have done any of that.
Yeah, so for our majority of experiments, we just throw the prompts encoder away. So that's like a pure automatic setting. We just have the encoder, decoder, and then that's it. And as I just mentioned to the last question, we did try some variation of actually keep the prompt encoder and throw additional prompts during the training, but we find that's not helpful. When we compare to that, we throw the prompt encoder away and just do purely fine-tuning. And regarding your second question about combining with NUNet, I think then the question is about how do you integrate the prompts into the NUNet framework. I think it will be helpful in the end, and yeah, but then that becomes a different question of you need to basically provide this prior manually to each data set. Then probably you should be expected to get some performance improvements.
Okay, perfect. Thank you.
Thank you.
One more question?
Thanks, very nice talk. And I'm curious about the results, about the performance. So do you want to share, or do you have any thoughts about why using the efficient fine-tuning is better than the vanilla fine-tuning?
Yeah. So let me go to this one. Well, I'll just explain. So I think that really depends on the data size. So if your backbone is small, so for example, the VITT, the tiny one that only has 4 layers, you do see that the vanilla fine-tuning, that you update all the parameters, was comparable to the parameter efficient fine-tuning. But when you have more data, the parameter efficient fine-tuning works better. I think that's likely because of the size of data. We just collect publicly available data. That's just ranging from a couple hundred slides to at least, I think, 10,000 slides being available. So I don't think that's enough data to train a huge model like the VITH. So in those cases, if we reduce the number of trainable parameters, right, we only train the additional layer from the parameter efficient fine-tuning. I think that is sufficient, but not sufficient enough to cover, the entire model.
Yeah, I see. Thank you. And I wonder for a single data set, because this is the average over 17 data set. So for a single data set, if I have, let's see, 100 subjects versus 1,000 subjects, so do you think is there going to be a big difference with such method?
I think you can actually find it out in the paper. I can't tell you because I also don't remember, but I hope it will.
Okay.
Yeah.
So what about the size? Not the sample size, it's about the target region size. Some of them are really small, some kind of big, like the liver or the stomach.
Yeah, I think it does matter, but I feel like let me think. Well, I don't think that just performs the same, I would say, as the UNet or other UNet families. For larger objects, it's easier, and for small objects, it's more difficult.
Okay. Yeah. So have you ever tried about the transfer learning, use the fine-tune sound?
I mean, all of our works during the setup 2 and 3 can be sort of as some level of transfer learning. You first continue pre-train the SAM with some medical data, and then you just really transfer it to a single data set. You can, yeah.
Oh, no. I mean something like a domain shift. So if you
I see. No, but my answer is I don't think that will be working. Once we fine-tune the model to one data set, the model can only do that. And it won't work that well for other modalities, even if they have the same target.
Thank you very much.
Yeah, thank you.
All right, I see no further questions. Just allow me one quick second to invite everybody to submit to Melba. I especially want to point out that after a couple of weeks after the SPA deadline in August, there's not a lot of deadlines in our field for conferences up until the MIDL deadline in December. So if you have a paper in the next couple of months that you're looking for a happy home for, consider the journal to conference track, and you can present at the next MIDL. With that, let's thank both of our speakers again. And shuttle is at 6.